event today and tomorrow, which is this distinguished instructor short course by the SEG, the Society of Exploration Geophysicists, on electromagnetics. And it's even more of a pleasure for me to welcome Doug Oldenburg, our instructor, our distinguished instructor today and tomorrow. And he is supported by Lindsay Hege. Doug Oldenburg, for those of you, I guess those of you who are in geophysics have come across his name anyway. But actually, for me personally, it's really a great pleasure having you here today, because as some of you know, also when I was kind of starting with thinking about inversion approaches, schemes, and so on, that was in DC resistivity at that time. Of course, I also went through your papers, and that was always providing lots of insights. And so although we had not met at that time, you have been a very important tutor for me and also for my career when I started. And so I'm glad that you today and tomorrow share kind of your insight and broad overview on electromagnetics. And that basically means covers the full range of electromagnetic methods. And I guess you talk about that more, the scope and so on in a minute. But I'm glad that also PhD students, as I see, have shown up, because I think this is a very excellent opportunity to kind of get an idea what electromagnetics is about, the theory, but also what it offers in terms of applications. And we're going to have 2 days. So today is the course, which basically means an overview of what I've just said by Doug Oldenburg. And I don't know, Lindsay, are you also presenting?
I'll jump in a couple things.
Okay. And then tomorrow is the DISC lab, which I think you will also explain perhaps in more detail than in a minute. So, but the idea of that is, for those of you who are also staying tomorrow, to really kind of explicitly work on some exercises. We'll have another room over there where we have access to computers. And so I guess that's also a very nice opportunity to kind of get experience in this framework. Okay, maybe what else? One word on the schedule. So it's quite flexible. I guess you welcome any sort of kind of feedback, questions, and so on. So let's have this in a very kind of active environment. And we'll have breaks. We have outside, the coffee break will be at around 10:30, but we'll see how it goes. We have coffee, drinks, snacks outside. For lunch, we'll have a break. I don't know how long it is right now, but so there is nothing organized. So just kind of organize yourself and just go outside. There's a number of restaurants, places, and so on, just within walking distance. And anyway, we'll make the announcement when we will kind of reconvene here then, I guess, before we break up. That's it for today. It's going to be the full day, so probably last until 6. Okay.
Yeah, are you guys ready? Yes.
Okay. I also have to say we have little technical problems here, so we hope that the technician comes in within the coffee break and kind of comes up with a more kind of sophisticated microphone, because it's of course not easy to kind of talk for 10 hours or 8 hours or whatsoever. So this is the reason why you see this sort of cabling. Okay, so with this, I think I give over to you. And so once again, welcome to Doug Oldenburg, to Lindsay, and we're looking forward to a very insightful 2 days on electromagnetics. So again, welcome.
Thank you. Okay, so thanks, Andreas. That's really great. And it's really great to see everybody here. And actually, it's really good to be in Germany. So we're taking this DISC around the world. We hit a variety of countries, a variety of levels of backgrounds and applications, and we're at the same time trying to offer something that's useful for everybody. And yeah, it's particularly interesting to be in Germany because Germany has got, I think, overall one of the highest standards for electromagnetic backgrounds and the research that's been done here. So it's good to see if we can present something that maybe you haven't seen before, and if we can't, at least to absorb from you all the things that you're doing so that we go back and enrich. So it's things like this are always a two-way street, right? You give a little bit and try to take away a lot. So before we do that, I'd really like to go around the table and get a sense of who people are and basically what you're doing and what you're interested with respect to the course. Importantly, what we're going to try to do today, this is really ambitious. We're going to try to look at electromagnetics all the way from square one, from DC resistivity, right through to GPR and do the complete spectrum. And I would like to kind of get some feeling for who the audience is, what you're interested in. We especially have case histories, and for many, we've got too many case histories to actually present. But if I can tell from what people are interested in, I can maybe glean some idea about which case histories we could present and which we could leave out. So with that, can we just start? Yeah?
No, we can start here in the back.
Okay, yeah, so there's right at the very back. And having just come in. So you just tell me your name and like whether you're a postdoc or a prof or a student, and what your background is and what you might go through.
Okay, my name is Hilda Ox. I'm working at the MIT University as a PhD student, and I'm working mainly in ERT modeling, so DC geoelectrics on a small scale, so also for the surface ERT, so that's what I'm interested in at the moment.
Okay, perfect.
So, my name is Igor Dalbo. I work at the Forschung Center and I mainly work with EMI, GPR, and I'm working currently on weather characterization. So, yeah.
Hello everyone, my name is Sigurd Khan, and I'm also a PhD student in Forschung Center Munich. My major topic is electromagnetic induction EMI, so I'm interested in doing fault modeling and inversion.
In any particular area?
To mean the field. Yeah, so use the EMI to measure the field. Yeah.
Okay.
Yeah, my name is, and I realized that I actually had forgotten one of the I apologize for that. So my name is Andreas Kemner. I'm head of the geophysics group at the University of Bonn, and I'm working on the use and also development of geophysical techniques mainly for near-surface investigations related to hydrological and environmental issues, and so started with DC resistivity, worked a lot on IP and also some GPR and also magnetic resistivity actually. So that's the background, and the other thing, actually more important, I think although I of course know very well actually where Doug is from and so on and about his achievements, but I think I actually didn't mention that you're from UBC. So Doug is professor of geophysics at the University of British Columbia, where also Lindsay is doing her PhD. And so I should add that, and I'm sorry for that, Doug. And he has been working on for decades. I think as far as I remember, you've always been to me actually at UBC, actually at this place. So kind of not moving around, but actually being in that place and from there developing. Like when I stepped into the field, that was like in the early 90s, it was already when these guys were kind of taking inversions from these kind of very coarse, blocky models in the 80s and so on to finer parameterizations, higher dimensions. And I mean, this guy has always been one of the driving forces, taking things from 1D to 2D to 3D and thinking about also with kind of very competent co-workers. I know remember some mathematicians coming up with the right schemes and algorithms, taking it to IP and of course the full electromagnetic spectrum, looking at the merging of methods, so gravity, magnetic, joint inversion with EM. So I mean, you'll find such a bunch of papers, and you will also, I recommend to look at the kind of chapters in some of the very good SEG books, volumes, like the one on near surface investigation. So you'll find, kind of some of the work that DEC has been contributed to the community. So sorry that I actually was thinking of the disk and so on, but I forgot the okay, so that's it.
Hi. My name is Frederick Nguyen. I'm the head of the Applied Geophysics group in the University of Liège, which is 1 hour and a half from here. And I would say that I work mainly in, let's say, environmental geophysics lately. And my interest goes into, let's say, inverse problems and data simulation, like for hydrogeophysical inversion and that type of
Hi, I'm working on this. I'm a PhD student from the University of Liège. I'm working in a team with Fred, and I'm working a project of integration of hydrogeophysical data in a multiple point statistics framework. So, by basically any kind of data, hydrogeophysical, it could be GPR, IP, to be integrated in this multiple point statistics framework.
Hi everybody, my name is Thomas Kremer. I'm a postdoc at the University of Liège also. My project is basically on groundwater characterization. I'm working on two phases. One is doing IP, trying to characterize sparkling water springs. And the other part is doing nuclear magnetic resonance and mainly trying to improve the signal to noise ratio in the European, how to say that, geographical settings. Like we have a lot of anthropological noise, I guess, from power line and all this stuff. It's quite hard to get NMR signals in these conditions, so we're trying to improve that.
Hi, I'm Florian Wagner. I'm a postdoctoral fellow here in Bonn. I've been mainly working with electrical resistivity monitoring, mainly in the cross-level setup, on groundwater salinization and CO2 storage. I'm interested in the dynamic processes and also hydrogeophysical inversion. But yeah, now that I'm here in Bonn, I've learned a bit more about SP and IP, but there's still a lot of in the electromagnetic spectrum, like inductive sources, time and frequency domain, EM, GPR, that I haven't been working with, and I'm really interested to learn more about that.
Hi, my name is Itzel, and I just started a PhD at the University of Liège. I'm going to be doing a geophysical characterization of landfill. So this electromagnetic variety of techniques is going to be really useful for me.
Hi, my name is Shari van Trick, and I'm working as a PhD student in the group of Andreas Kenner. And I'm working with SAP and DRT to investigate the root zone and root systems.
Hi, my name is Steffi, and I'm writing my master's thesis now here. And I'm very interested in what you have to say about the electrical resistivity tomography and what it can provide and what it can do.
I'm Jonas Limrock, and I'm a PhD student here in Bonn at Chemnitz, and I'm working on SIP for permafrost in alpine environments. And yeah, we try to characterize ice content and the permafrost from lab scale to fields.
Hi, I'm Maria. I'm a PhD in Munich as well. I'm using DRT, AMI, and GPR for monitoring changes in agricultural fields.
Hi, I'm Jessica Butler. I'm a student here in Bonn, also writing my thesis at the
the moment. I'm mainly using ERT, and at the moment I'm interested in linking those measurements to petrophysical properties.
My name is Yu, and I'm also the PhD student in Philosophy English, and my project is about the forward-forming version of GPR data and to try to use the inversion to get the conductivity and permittivity of soil.
Hello everyone, my name is Jun Zhou. I'm a PhD student in Photosynthetic English. My project is about forward-forming inversion using the cross-hole GPR. Thank you.
Hello, my name is Rea van Milo. I'm a PhD student at RWTH Aachen, and I'm using time-lapse ERT to characterize aquifers.
Hi, my name is Uta Sauer. I'm from the Helmholtz Center for Environmental Research in Leipzig. I'm more involved in projects related to characterization of the near surface. And so we applied several kinds of geophysical methods. At the moment, my focus is more related to geoelectrics, self-potential, and seismics. But I think 8 years ago, I was more deeply involved in writing a SEN workshop about electromagnetic induction for near-surface applications. So I try to catch up a little bit what is the state of the art now and hope to find, okay, let's try again, electromagnetics.
Good morning. My name is Thomas Fettner. I'm with company Geotomography, which is close to Bonn, my lead. I would say I'm a bit of outlaw in this group because I'm totally focused on seismics. I heard my last lessons in EM with Andreas Vella was 30 years ago. So I'm curious to see if there are any news.
You'll be very happy to know that not one of Maxwell's equations has changed.
Hello, my name is Michael Ekman. I'm a bachelor student at the University of Freiburg. And we didn't have much modules about electromagnetics, so I'm very interested to hear about it.
Hi, I'm Christine. I'm doing my PhD at Ghent University in Belgium. I'm working at the Department of Soil Management, and my project is about the characterization of landfills. And I mainly use EMI techniques. And I'm interested in 3D forwarding of the data.
Hey, my name is Stephanie. I'm a research assistant at the research center in Munich, and I did my master's there before. And while I was doing my master, I did a lot of research regarding peatlands. And in peatlands, I used cross-hole ground penetration radar measurements to figure out all about the soil properties in peatlands, and then I used full waveform inversion, small scale detail view or image. Yeah, now I'm interested in also the other EM methods, and hopefully I will also learn more about inversions.
Hey everybody. I'm actually working in Portions and Community as a PhD. I'm working on a GPR full wave inversion cross-hole and developing 2.5D full wave inversion, and I'm done on it.
Hello everyone, my name is Berek Rose. I'm a PhD student in Portions and Community Center in English. I'm working on GPR using full waveform inversion to characterize aquifer.
That's great. You're going to be good at this. There's a lot of different backgrounds here. You're also everybody's kind of up at some at some reasonable levels with respect to these things. ERT certainly very predominant. IPS, I'm looking for at SP and GPR. Those seem to be the things that are kind of coming through. Some kind of chemicals in there for various kinds of electromagnetic induction, and I think that there's opportunities to kind of put all of that together. So that's perfect. Where'd he go? Pardon me? Oh, okay. Well, there's a little bit of a delay. Does that work?
This one's not. That one is.
Two mics, there's a sort of an echo.
Well,
Yeah, there's a bit of an echo.
We'll stick with this one.
Who would have ever thought you'd have a technical delay in Germany, right? So those of us who live in North America, you know, we've got Germany on this kind of pedestal, right? Where, you know, if you want anything done and done right, you talk to the German engineers.
How's that?
Is that good?
Yeah.
I mean, it's not such a big room, but honestly, after talking for 8 hours, the throat gets a little sore, and also, unless there's some energy in the voice, then people tend to kind of nod off, and that's the one thing you're not allowed to nod off. Well, we'll try that. That's my response. Anyway, so the SEG every year asks somebody to go around and give a course on something. This year, it's on electromagnetic geophysics, and we're taking it to a number of places around the world. And here's our stop in Bonn. Before I start, I really want to thank two people who are really instrumental. I can tell you, if you're trying to organize a worldwide tour and you're sitting in one country and you don't know very many people in a particular country, the most important thing that you can have is a local host. And I really appreciate everything that Andreas has done, and also for the work that they've done in trying to organize our trip here and to get people here and see if we can be effective, because that's our role here. We want to come. There's a lot of effort that we're putting in, but we want to leave at the end of tomorrow feeling like, okay, we've somehow made a difference here. Before we start, a little bit about yourself. Maybe it's worthwhile telling you a little bit about me. I was a student many years ago. My supervisor was a guy named Bob Parker, who did some of the fundamental work on inversion, and he was actually mentored by two other people, George Backus and Freeman Gilbert. And I had the exceptional opportunity to be at Institute for Geophysics and Planetary Physics in California with them. And so that's where I got my basics, and that's where I got my inspiration to work on the inverse problem. To put things in a historical perspective, in about 1975, perhaps a little bit before your times, the type of problem that could be solved is something with maybe 50 variables. So that meant the 1D DC resistivity MT problem. Roll it up to a decade later, 1985, we can solve the 2D DC resistivity and IP problem, maybe with 1,000 problems. The next step, so you go 1D, 2D, 3D, the problems that we can solve: gravity, magnetics, DC resistivity, IP, maybe 100,000 variables. The big leap was to the 3D frequency and time domain problem with just a few sources. That's about that. A major advance came in this time period here, where people realized you could factor these very large, sparse matrices and basically use direct solvers. Couple that with multiprocessors. By the time we get to 2015, basically we can solve 3D frequency and time domain problems with lots of them. So that means that with the advances in computing power and the ability to solve the inverse problem, that we can now solve virtually every EM geophysics problem around. The next advancement has really been in instrumentation and data. And we can now acquire unprecedented data both in terms of quality and quantity. And you can have big data sets for California coast, for instance, we're looking for water. Here's hydrocarbon, or so seafloor EM, risking, and then you get some continental wild stuff. These are MT stations covering the Australian continent. Third element, web and open source resources. This has been huge, and this is all, most of this has come about in the last decade. What it allows people to do is to interact and collaborate, share, test things. And we've developed something called SimPeg. The group here has developed PyGimli. These are open source resources that can be shared and used for computing. And then the fourth application, or fourth thing, is many applications. So, and if you look around, we've got a huge number of problems, right? We've got minerals, we've got contaminants, just water issues and all kinds, geothermal energy, unexploded ordnances, hydrocarbons, slope stability, geotechnical problems. There's tons of problems that are out there. So if you think about these basic ingredients, we've got problems, that's important. High quality data, ability to invert the EM data, web tools to communicate. I mean, we should be good to go. So the question is, what's the roadblocks? Well, there's a lot of them. In general, geoscientists, first of all, they don't really realize what the role is that EM can play in helping solve their problem. They're just not connected with it. And they don't understand the technique. The technology is confusing, right? These EM guys go talking about their real data or their imaginary data or whatever. It's not like seismology where things are really understandable. And the EM data they're complicated and they're unintuitive. This makes a huge impediment to really trying to use them. The other aspect, and it's a really important one, is what is the connection in my problem and the physical properties of interest? Because that's the only way, if we're working with a groundwater hydrologist or we're working with a geologist or something, we always have to be able to translate the problem into something that talks about an physical property, and that's a hurdle. And even if you decide that, okay, well, I could go ahead and use EM of some sort, then which type of service do you use? What do you choose? You want DC resistivity, you want something in frequency, time. Where should your sources? In the air, on the ground, downhole. And then what to expect for resolution? Understanding that business is really important. And then maybe lastly, are there situations similar to mine in which GM or electromagnetic system? That's one of the great things. If you got a problem, you can find out an example where somebody else has had kind of the same problem and it's worked, and you're like, it provides a level of confidence. So those are the roadblocks, and that's what we're going to do. That's what we're really going to try to do between today and tomorrow, is just get rid of all that stuff, make things really understandable, and move on to actually using electromagnetics. So, you think we've got everything, and this is the reason for the disk. Here's our symbol for the disk. So we've got the problems. We've got high quality data. We can invert everything, and we've got web tools to communicate. So the disk is kind of situated in here. It's like a perfect storm. It's a perfect storm, almost. It's a good idea, but it's missing one important ingredient. What's missing? What's missing?
People?
Pardon me?
People?
People. Exactly. We need a bunch of bright young people, of which there's lots in this audience. And I've got two who come with me as co-presenters. There's Lindsay and there's another guy named Sagi. And that is the missing link. We put all of those together. We really should get it going. So the goals for the disc, I'd like to inspire you. You could do that by just showing the variety of applications and illustrate the effectiveness of those by using case histories. Build a foundation. You've got to understand the basics. So what are the principles of EM? We're going to try to help with those by looking at a variety of interactive apps that will visualize things and allow you to ask questions. And we've spent much effort into developing an open source resource here, EM GeoSci.xyz. Want to set realistic expectations. If you over expect something and underachieve, it's very disappointing. And you have to realize this can play a role and at what scale it can help. And the last part, and this is really important for us, and that is that we want to be part of developing an EM community. It's only by kind of working together that we can really advance the field. And so the advent of open source software, which Gimli and Florian has been doing with a number of other people, and capturing case histories worldwide, being able to kind of talk to each other and know what other people are doing and try to have material so that, especially as an incoming graduate student, you're not rediscovering the wheel, spending 2 years of your life just getting up to speed onto what the real problem is. So those are our goals. Just briefly about the EM resource. How many people have seen this particular book? And also there's a chapter there by Ward and Holman. It's edited by Lisa. Just put your hand up if you've seen it. Yeah, 1/3. So there's a chapter in here which is kind of a Bible for people who are doing electromagnetic geophysics, and it's got all the equations, different kinds of geometries. Honestly, you really learn a lot. However, what we're trying to do is to basically take this material and bring it live into our resource. Our resource page has got a number of things, including fundamentals, but it's also got case histories that will make heavy use of. And we're going around the world trying to capture these. The case histories, we've parsed them out into basically a 7-step framework. And I think anybody who does any applied problem will kind of think in the same way. We first of all have a setup, but what's the problem? And then what physical properties are we interested in? What survey do I choose? What data do I collect? What processing has been done? What's my interpretation? And what's my synthesis? How does that impact upon the problem? That, I think, is the way that most people would parse out their problem. The advantage of doing this very explicitly is that it really promotes communication. Because if you're talking to me about a particular problem and it's kind of in this framework, then I can sort of easily see where we are, and it's easy for me to kind of step in and look at things. So these are all kind of crazy works, but they act as very nice summaries and a very nice way of being able to communicate with people about their particular problem. And these things, they can be edited interactively, work with GitHub, open source, stamps of approval. And then I mentioned apps. My group at UBC has been actually working for a couple of years on developing these interactive apps that promote education. And more we're steering towards in courses just to basically start with an app that shows the ability to model and see what the responses are, what the fields are, just to kind of work with that. Because really, if you look at Maxwell's equations, it's like, okay, I got it, time-varying magnetic field gives it electric field. But that's only a certain part. But if you're actually able to go down and put something, let's put an electric dipole in the earth, and you're able to change the various parameters of frequency, and partition out the real, the imaginary part, and just do things so you can ask questions. It's a great learning tool. So how are we actually going to achieve our goals? Well, first of all, I'm going to connect to relevant applications, select a particular type of survey, use the app to explore and ask questions, and then try to show the success. The agenda for today, honestly, we're going to start right at the beginning. So I think some people might find that, well, that's pretty elementary. And it is, but it's also important. So we're going to start with DC resistivity. There's been a lot of people who are doing ERT here. And then just something, refresh your memories about what is EM induction. And then we'll look at inductive sources. So those are generally airborne kinds of problems, but they could be on the surface of the Earth. At lunch, there might not be time to play with apps, but that's basically where we're going to be. In the afternoon, we're going to start off with grounded sources. That's where the marine EM problem plays a role, or then natural sources, maybe tellurics, and we'll go to high frequencies, GPR, and induced polarization. And talk about the That's a lot of stuff, but we'll try to be efficient, and I think we can do it. And if we can do it, the advantage of this is that you then see electromagnetics in the full perspective. And for some reason or other, that just really, really helps you trying to figure out, if I'm going to apply EM, where should I be on that spectrum, and what can I get? So it's very, very useful if we can just kind of step back far enough so that we can see the whole picture. So there are people in here who are very expert, Andreas, Florian, others. I don't know, what I'm actually hoping that even for these people who are experts, that there is still something here. And I go for coffee every Saturday morning with my wife. We go to a specific coffee shop, and we meet the same friends. We tell the same jokes, we order the same coffee. We've been doing this every day for 23 years, every Saturday, without fail. And they always have a saying as you're going into that coffee shop. And we ran in one time, and I thought, this is perfect. Because this is what it says. That is what learning is. You suddenly understand something that you've understood all of your life, but in a new way. And that can actually make a difference. You can know something, you can understand something, you can work with it, and then suddenly you see the same thing being offered, and there's just a little few tweaks and twiddles around, and it just enriches your fundamental understanding about what is going on. So for those people who are expert, we're going to resort to this. Disc Lab Day. The Disc is a 2-day event, and it's a bit complicated, and if people have had challenges trying to figure out, is this a 1-day event, is it a 2-day event, we completely understand. The SCG sponsors a 1-day course. It's actually supposed to have a book written, but we decided that there's no reason to write a book. If you write a book, the moment that you close that cover, it's out of date. So we're not having a book, we're having a live resource that can be completely augmented. The other is that we have other goals here. We want to find out what problems you are working on. We kind of went around this morning, but tomorrow at Disc Lab, we're going to ask people to make a short presentation. Stand up, 5 minutes, grab a couple of slides, just tell us what you're working on. We capture those on YouTube, providing you're amenable to that. And then as we go around the world, we've got these different places where different people are working on different problems. And, you know, it's just really interesting. You're thinking about, oh, what are geophysicists in India really concerned with? What kind of techniques, what kind of problems, right? And then you could go to our blog that we have and just look to see what happened on Disc Lab Day. And you can find out who was talking, what their problems were. It's great, and it's a great form of, it's great motivation to kind of communicate with people like that. So that's our goal. So tomorrow is actually going to be a multi-fold event. First, there's going to be a little bit too much material for us to cover today, and so we'll do a little bit of that tomorrow morning. And also, there's certain things that are a little bit more in depth, like there's items like EM coupling removal from IP data, or there's just a whole bunch of other case histories, and we could talk a little bit about them tomorrow, as well as capturing what you are doing. And then the other aspect that we would like to talk about is SIMPE, our open source software, and the programming a bit around the apps, and also kind of an introduction to inversion and modeling and simulation. There's a lot of potential here, and we're going to try to find out what things you're interested in, because I said what we want to do is do things that make an impact. So we need a little bit of your feedback about what extra kinds of things that you'd like to talk about. So there's resources for there's our open source GeoSci. There's also something called Slack. How many people use Slack? About half a dozen. So this is a way of communicating, asking questions, just posting pictures, just talking to the group. We'll show you a bit more how to get connected with that, so that we can all have a Slack channel for Bonn. And we're asking people to contribute to GeoSci and case histories and content, and also to SIMPE and our software. And one of the big things that we're really excited about here is is interacting with Florian and people who are doing PyGimli and see, SIMPE, PyGimli, maybe there's other things out there. Let's all find some way of putting it together, and so that advance the use and usefulness of electromagnetics and computation. So I'd just like to kind of start things off a little bit. We're going to do a short introduction here. Just as a way to kind of ground us, there's three problems here that are listed. There's the mineral problem, unexploded ordnance, and water. And the reason I put these up is that each, a prime physical property connected with each of these is that with minerals, it's often electrical conductivity, unexploded ordnance, both electric conductivity but also magnetic susceptibility. And with water issues, namely conditioning of yard. So just to make sure that we're all on the same page, first of all, electrical resistivity. So the resistivity of a rock kind of codifies how easy it is to put current through. Oh, thanks for it. That's a lot there. How easy it is to put current through it. So rocks that have a very high resistivity don't pass current very easily. So that could be like igneous rocks up here. Rocks that pass very easily are way down here, say massive sulfides. So you can see there's huge ranges. There's like 6 or 7 orders of magnitude different here, so it's a big, big scale. And a lot of the rocks that we deal with, clays or sandstones, they kind of fall in this 10 to 1,000 ohm meters. So that's resistivity. The other word that we'll use is the reciprocal of resistivity, which is conductivity, and that's in Siemens per meter, or sometimes millisiemens per meter. So a rock that has very high resistivity has a very low conductivity, and vice versa. As an EM person, we tend to use the words resistivity and conductivity almost interchangeably, sometimes even in the same sentence. But you just have to remember that and live with that kind of quirkiness. The other physical property is, electrical permittivity or dielectric constant. And here, the major contributor is any kind of water, fresh water, seawater, has a value of 80, air has 1, and everything else is kind of in between. And magnetic susceptibility also varies over many orders of magnitude, with magnetite being up here at the sort of the big kid on the block, and sediments or metamorphic rocks often having very low magnetic susceptibility. With all of these, the generic geophysical experiments want to have a source, they're going to input some energy, and then depending upon its conductivity, susceptibility, electrical permittivity, there's going to be a response. The signal is going to come up, we're going to measure it. This course is not math heavy by any means, but we are going to look at least at Maxwell's equations, which here they are written. We'll come back a few times during the course and just try to kind of garner what we're looking at. There's Faraday's law showing that change in magnetic flux gives an electric field. Ampere's law, current gives rise to a magnetic field. Then there's constitutive relationships that relate a field to a flux. So here's an important one. It's called Ohm's law. J is equal to sigma, electrical conductivity, times. Equations can be written in the time domain. We can also take a Fourier transform and write them in the frequency domain, in which they look like this. And in most cases, we'll be keeping capitals for frequency and small letters for time. But if we solve those equations, that's all we need. We solve those equations with sources and boundary conditions, you've got every electromagnetic phenomena that you can imagine. So, if you're going to do that, what sort of sources would you use? Well, we've got all kinds of things that we could do. We could use an inductive source, and when I say inductive, I mean that we've got some kind of a wire loop that's going on. There's nothing that's going to be touching the ground. And so here's a inductive source pulled by helicopter. We'll see a few of these during the day. Or we could have a grounded source where we've got maybe a generator in here that's attached to two probes. So that's our source. But we could also have different waveforms that go through. We could have a harmonic waveform, or we could have a time domain general kind of transient waveform. And then as far as locations, that source could be in the air, could be on the ground, could be in world. So that's a lot. Even when you just think about sources, there's a lot of potential here as far as different kinds of systems. And what about the data? Okay, so we have source, interacts, gets the data. Well, if we've got a harmonic signal, then we could measure an E and a B. in frequency or time. But then there's the question of, okay, well, which field are we going to measure? We're going to measure E field, the B field, dB dt, which ones? And then which frequencies? Low frequency, high frequency, or in the time domain, we're going to have a decay, and then which time channels do. So our magnetic receivers, will have something on the ground that measures that, and then for our measuring the electric, we basically just 2 probes in the ground with some kind of voltmeter. And then, as you can see, these are fields, so they're multi-components. So you could measure, an X, a Y, or a Z. So which components you really want, and then also again, where's the location? So in the air, on the ground, etc. So if I come back to those 3 problems, the one thing that is interesting is that electrical conductivity is actually applicable to all 3 of these. So if we're going to start to look at electromagnetic induction, at a first stage through, conductivity is going to be very important. Towards the end of the day, electrical permittivity, GPR, will become important. We're not going to do very much at all in this course on magnetics, although we certainly could, because there's a lot of really interesting stuff. So what I'd like now to do is to do the DC resistivity. Somebody can ask questions or make a comment if you like. This is supposed to be really cash, right? So. Whoops. We can see this tomorrow. This is all about IP, and some of the stuff that we've been doing for IP, especially removing EM coupling and then seeing what we got. It's interesting. Luxury 3-room bedroom apartment available in 10 minutes. I just flashed up on my screen. Let's see what happened here. Bonn. No, I think we're okay. Not sure what happened.
Here, just minimize this guy.
Sorry?
Just minimize. And then click on your slides here. Yeah, there you go.
Okay. Perfect. Okay, so there was quite a few people that have done ERT, so you may be pretty much familiar with this, but again, we need to start at the beginning, and we need to start so that everybody is on the same basis. And if we've got some people here who don't really know very much about it, we need to get everybody up to speed. So the DC resistivity, we've got energy source, we're going to put in ground. We're going to look, I'm going to try to keep most things in terms of resistivity as opposed to conductivity, but sometimes we'll change. And that is the target that we're looking for. So what's our motivation for this? Well, there's certainly mineral exploration, water, especially in mining environments. We've done some work in potash mines, oil and gas, application for groundwater. There's geotechnical issues. There's a whole host more that we could put on, but that's enough to realize that there's a wide spectrum. So we saw this before, DC resistivity. It's going to be sensitive to different kinds of rocks. We showed this image before as far as resistivity as a function of rock type. The thing that's important here is the factors that DC resistivity depends on. So it depends on the rock type. Excuse me. Let's see, I wonder, is there any water that somebody could grab me a glass of water? So it depends on many factors. There's the rock type, porosity. If we look at this particular rock here, then this is very porous compared to here. There's that connectivity of all of the pores, and then there's the fluid that's inside, and then there's the metallic content of the solid matrix. So here's a penny for scale, and you can see the variation that is happening over here, and you could start to realize that maybe the estimating the reason. Oh, thanks a lot. The resistivity of the rock might actually be a complicated thing. So we're going to talk about oh, thanks a lot. Some of the basics of the experiment. I'm going to talk a little bit about sensitivity, survey design. I'm going to show you a case history for mining deposit, and we also have a case history for monitoring dams. So what's the basis? What we got here? This is an ore body. There's a really low resistivity environment in here. That's the mineralization. There's a top on here that's quite resistive. There's a fairly conductive overburden compared to a host. So that's the guy that you want to find. So we're going to do a DC resistivity experiment in which we first of all have a generator. It's going to be hooked up to 2 probes here. And that's going to put current into this ground. And then we're going to have a measuring device here, a voltmeter. So the currents, as they flow into the subsurface, flow in accordance with what the nature of the conductors are, and so they'll preferentially kind of flow into a conductor. That flow into a body with a different conductivity ultimately results in the existence of charges that are on the outside of that body, and those charges via Coulomb's law build up electric potentials that could be measured at here. So that's basically the experiment. So the question then is, well, okay, so how do we obtain resistivity? Well, if we look at Maxwell's equations in steady state, then all the time variations goes to 0. So you actually end up with the electric field following this equation, so it could be written as a gradient of some potential. And we've got Ampere's law, which then becomes this. So J is the current to the ground, Js is whatever source we've got. And we've got Ohm's law. We put all that together, and we end up with one of the most probably important equations in electromagnetic geophysics, and that is that you've got divergence of sigma grad potential equal to some right-hand side. So if we happen to be in a homogeneous half space, then there's an analytic solution for that looks like this, which could be rewritten into a form that looks like that. So, okay, good, we got analytic solution. So how does that help us? Well, first of all, suppose that we have a uniform space and we just plug a current electrode in here. Then the voltage, according to this one, just sort of falls off like this, and you can see that I mentioned it because we have a uniform space. The current is just going out completely axially like that. And if we put a voltmeter here or could measure the electric potential, we'd get some number. And the thing that makes this interesting is that we could take the initial formula and we just simply rearrange it so that we've got resistivity here and related like this, so that if we knew the distance that we're away from the current, we knew the current, we knew the voltage, I would be able to predict a resistivity. In this case, the resistivity of this background was 500 ohm meters, and that's the number that we get up. So that's actually kind of amazing, right? You put a current into the ground, and you just sort of measure a voltage someplace out here, and you've actually got a relationship that tells you what the resistivity is. And it doesn't matter where that particular point is, you'd always end up with the same resistivity. We can't, of course, do that. We need to have a circuit, so that we need to have, like a generator needs to have two ends on it. So we're going to always have, here's our current generator, and we're going to always have the A electrode be positive, the B electrode be negative. And if we looked at what happens if I take those currents and I put them, see, oh, well, of course, they go from the positive electrode to the negative, and they go in some kind of pattern that looks like this. So here's what my potential would look like. If I measure the potential difference, so now I'm going to have a positive, and my potential meter here and here, then I can use that potential difference to find the resistivity. So first of all, from the forward perspective, that potential difference is given basically by the same equation that we had before. It's just that the distances between individual electrodes changes, but that basically comes out to a geometric factor. And then we rearrange and we do the same thing, and we got the resistivity is this measured potential difference divided by that. So again, it doesn't matter where those points are, you're going to get the same value out here. And notice that this apparent resistivity is 500 ohm meters, which is what the true value is. Okay, so now what's going to happen? What's going to happen to this picture if I, let's say, put on a bit of a conductive region at the top? So instead of having 500 ohm meters here, I'm going to put on a little layer of 100 ohm meters. What's going to happen? Anybody? Yep.
There was a build and current may flow in the more conductive region.
Right. So if we put something on here, current tends to flow in regions of more higher conductivity. So if I do that, then you can see that there's preferentially more current in this top layer compared to the layer underneath. If I now use the same formula, I get apparent resistivity of 226. So it's not 100, which is what the top layer is. It's not 500, which is that. It's some kind of blurring of these. And for that reason, it's called an apparent resistivity. It's not a true value. It's just apparent. It's a way of kind of understanding what the data would be like, if what kind of half space would be there to reproduce that data. So we have some apps that allow you to do that. Allows you to put in a layer in here, various thicknesses, various conductivities, and change the locations of the potential. You can see the current lines that are going through, and it just helps understand. Play around with things and ask yourself some questions, and you can plot the potential, you plot the electric fields, you plot the currents. I want to talk just a bit about how data are collected, or at least a lot of data are collected, and that is through different kinds of soundings or arrays. And one of the most common is something called a Wenner array, where you've got the 4 electrodes and you kind of got equal spacings in here. Or there's a Schlumberger, which is basically the same thing, except you tend to have a smaller spacing to measure the voltage. what you're ultimately going to do is to try to get a curve, it's called a sounding curve, that relates the apparent resistivity to the size of this array. So you can start to set up some intuition for what's going on by thinking about that previous problem where we had a conductive layer at the surface, and now I'm going to take my two current electrodes and I'm going to put them real close together right near the surface. So now you can imagine how the currents are kind of going, how they're flowing, right? They're primarily going from, you know, one electrode to the other, but they're all kind of confined in here. There is some stuff that's coming on here, but the voltage that you measure is such that when you calculate the apparent resistivity, it's about 100.3. So your whole array is really tiny. You're essentially just kind of concerned with that top layer, and your apparent resistivity on your is basically the background 100. Well, the layer value. If you increase the spacings, now you're starting to look deeper. Okay, you get more currents coming in here. Your apparent resistivity increases to 135, and there you are here. And you increase it more yet, and now the currents are going deeper. Now you've got apparent resistivity that's 239, so you're up there. So in summary, the idea is that somehow the scale of your array is connected with how deep you are seeing. And perhaps an important takeaway point here is that, for instance, if you look back here, the distance between the two current electrodes was 60 meters. Thickness of the layer was 8 meters, and your apparent resistivity is still only at 230 meters. In other words, if you're trying to see something at depth, and we'll come a little bit more towards that later, the scale of your electrode array has to be considerably larger than the depth of the target that you're looking at. So this is that's a data plot. What you're really interested in, so there's an apparent resistivity, and this is not depth. It's just got something associated with the scale length. So that's just a way of plotting data. So what you really want to do is invert the data. So somehow you want to go from the data that you've got to this inversion package. Give you that. Most of my life, I've actually spent kind of working in this domain, and there's a lot of stuff we could talk about with respect to inversion. Some of it we could postpone a little bit for tomorrow. For today, I just don't want to get into that. Too much to be done. But basically, the general idea is going to be that we could take an Earth. It could be a 1D, 2D, 3D model, doesn't matter. Divide it into a whole bunch of these cells that are, each one has got a uniform value, but you don't know what that value is. And then you've got an algorithm that adjusts the values of those parameters until you not only fit the data, but you fit whatever other a priori information that you've got. So let's now, for today, just assume that, okay, we can somehow do these processes, even though some of them might be computationally quite complex, especially when we talk about airborne EM inversion. So let's concentrate just a little bit on a subject that is pretty important. So we talked a bit about before. So I've got currents flowing in through here, but it's steady state. So the normal component of that current density must be continuous. But the normal component of current density is given by Ohm's law. So J is equal to sigma times E. So that on this side of the body, we have sigma 1, there's an electric field E1. On this side, sigma 2, an electric field E2. But if the conductivities are different, So if sigma 1 is not equal to sigma 2, that means that E1 is not equal to 2. So what is the physical phenomena? Maybe don't look at the screen. What's the physical phenomena that that is associated with a discontinuity in the electric field? So suppose you're coming along this way, and then suddenly you've got a discontinuity of the electric field. It changes right here and then over there. So what's the basis for that? What's happened physically?
Snap.
Pardon me?
Snap's law.
No, not really. It's not what I'm looking for. So what's... Anybody? Oh, you're so shy. In either. I see your name is?
My name?
Yes.
Stephanie.
Stephanie. Okay, Stephanie, what's going on?
Oh gosh. I think it makes a jump there, but I don't know how the word for it. It comes in, the current line comes in here, and it makes a little jump, and then it moves on there, but I don't know the name of it.
So that was interesting. So you mentioned Snell, you mentioned current making a jump. Very often when DC resistivity is presented, people talk about putting everything in terms of currents, and you can do that. I actually like to think about charges. So if we come back here, if you remember the first year of physics that you do, you have charges that are put on a plate, right? It's a plexiglass plate or something like that. And you look at the electric field. So if you had a charge boundary here, then the electric field goes outward from that. So here it's pointing this way, here it's pointing this way. So if I'm looking at the electric field, this way, right? So I'm coming in, I get electric field that's pointing in one direction, and then suddenly I'm on the other side, it like changes direction. So the fact that we've got a discontinuity in the electric field means that we must have charges that are built up. And that is the essential element that is going on in DC resistivity. You have steady state, all the currents are flowing. There's nothing, complete steady state. And at any place where there is a difference in the electrical conductivity, there must be a charge. And if we have a charge, then we know through Coulomb's law that that's going to give rise to an electric field, or we could measure the potential difference. So we're going to see this a lot during the day because there's going to be electromagnetic phenomena that will have aspects of this DC resistivity galvanic currents that really give a signal that is related to these charge buildup. So we can see that here. So let's put in here a sphere, and now we've got an A current that's coming along here. And just as we had thought before, currents are kind of going to get sucked into a conductive object and then back out. So the currents are going to go from A to B but get distorted. The secondary currents are the total current that we'd have minus what we'd have had without the sphere. So they're like secondary currents, anomalous currents, they're kind of same. But look at these guys. So we see what they do. They kind of look like current dipoles, right? So the current kind of comes out here and then back here, out here, and back in here. The underlying quantity that's really driving everything is, if you looked at the charge buildup, so right here there is a change in that electric field, that there'd be negative charges on this side of the sphere and positive charges on that side of the sphere. And that gives rise to a secondary potential that looks like this. And of course, we'd be trying to measure that up here. Okay, so that's kind of what's happening. We got currents that are deflecting, we got charge buildup, and those charge buildups are giving rise to a potential, which we can measure. So what's going to happen if we attempt to, let's suppose we've got our sphere, we've got our current electrodes out here, and now we want to calculate an apparent resistivity. Well, if we do that, we have our, so we're going to put our voltmeter attached here. So here's M and N. And now this is the great thing about like thinking in terms of charges, because we just so understand, like, okay, I've got these charges here. If I'm sitting here, I'd have a negative potential that's going to be associated with these charges here, positive potential associated with these. They're closer to the negative than the positive, so kind of get a sense about how things are going to work. And here that the potential difference is actually going to be decreased from what you'd ordinarily have. And in fact, the apparent resistivity in this circumstance is 430, which is less than 500. So you're coming over here, you're measuring a low apparent resistivity, and that's because of these charges that are here and your potential output. So this is a slightly different thing. I mean, nothing has changed as far as the currents, but now, now I'm sitting out here. Here's my voltmeter. Still have the same charges, but I'm actually getting an apparent resistivity that is larger than 500. Not much, but it's larger. So now you're asked the question. Okay, so I take an earth, okay, 500 ohm meters. I put in a conductive body, measure an apparent resistivity. It's actually at some point it's actually larger than any number I got. So what's happening there? How would we understand that? Anybody? How could, I mean, why is it that in this configuration you could actually get a number that's larger than 500? 500 was the biggest resistivity that we have. Okay, you could think about that. We're going to have coffee. And we come back from coffee. I'm going to show you one app. That's about all we have time for. But by using that app, I'm going to show you how this is completely 100% intuitive, that you would then understand that. But you can think about it in the meantime. So here, this is what happens if we had this fixed currents and you moved over here. You'd have apparent resistivity that's high, low over here, and high. So yeah, you might be detecting it. The other thing, excuse me, is called profiling. So in a profiling, so basically just to summarize, maybe I didn't do that. So in a sounding mode, like I got to get right over by Stephanie. Okay, I'm looking right at you, okay? And I'm going to start with my electrodes that are really close. So your name is?
Pelik.
Pelik? P-E-L-I-K? G. Oh, okay. So when my electrodes are really close, I'm maybe barely seeing Pelik. I'm not, right? But now I expand my array and I get the second row, and then finally I can see you. And so I'm just kind of looking down here and gradually getting deeper and deeper and deeper. That's a sounding, okay? The other thing is a profiling, right? So if I start off with a system that's very small, now I kind of come along here and, I kind of see the front row. I see Peleg, but he's actually not changing from Lindsay, so I really don't see anything much happening at all, which is kind of what's happening here. So here's AB, here's NN, and I'm just kind of moving that along the top, and I'm just seeing what's happening right up at this surface here, and that is apparent resistivity of 500 ohm meters. Okay, so I've got a system. It only sees a little ways in. I move that system across. If there's nothing that's changing, I don't see anything that's particularly interesting. However, if I make the system bigger so that I actually now have a penetration depth that can see Stephanie, then we're in a situation that looks like this. As I come across, I get this up flank, and it goes down to 300 ohm meters, and then up like that as I go across. Again, notice these numbers out here that are larger than anything else. That would be one of the things that should probably catch your eye right to start with. Like, wait a minute, how could that be? And then, as I said, we'll use the app to help understand that. So that's basically it. We can expand, that gives us sounding. We can translate, that gives us a profiling. So if we've got something that's two-dimensional, we kind of want to do both, right? Because I've got, you know, something that, you know, I want to be able to. So your name with pink one thumb, yeah?
Réan. Réan.
Yes.
It's R-H-E-A.
How do you spell?
R-H-E-A.
Oh, Ria? If I said Ria, would that? Ria. There. No. Oh yeah. Sorry, you'll have to clear it up. So I'll just say Ria. Okay. So anyway, we're our goal is to find you, right? You're sitting there, and so you know I can set my electrode array and come along here. See, you know, maybe get down to Pellic. But if I make it a bit bigger, you know, I can get down to you and then see what's happening at your level. And then she gets out to Stephanie, right? So you kind of got the idea. We want to do profiling and sounding. There's a whole bunch of different setups that people, you can talk about Leonard Schlumberger, kind of talked about gradient array, where you basically set out your current electrodes, and then you just move your potentials everywhere in between. The terms that you'll hear a fair bit, especially if you're doing mineral exploration, is pole. Of course, you always have 4 electrodes, but you know you can run up one current electrode a couple of kilometers this way, and you can run a potential electrode a couple of kilometers that way. So effectively, you've just got a full pole, or pole dipole, or a dipole dipole. So those are terms that people tend to talk about. We now have to plot the data, and here's what we're going to do for 2 dimensions for this kind of profiling sounding array. Then we're going to try to make a plotting plane. So here's a dipole array, and we just want to plot that, right? And so traditionally, what's often done is take the midpoints, do 45-degree angles, and plot the apparent resistivity at this point. Then as this moves, then the plotting point moves down and continues to move like that. So what I'm going to show you here is building up a data plot, which we call the pseudo section. So how many people have not heard of the word pseudo section? Oh, okay. Well, then we could go through this quite quickly. Okay, so this is going to be a pseudo section that's built up by gradually moving this other potential electrode out this way, plotting it, and then translating the whole thing along. So we're just translating along, gradually building it up. Point. Okay, great. So there's your there's your pseudo section. Yeah, it's a plot of the data. There's low resistivities in red, high resistivities in blue. Might be telling you something geologically. Might just be an interesting plot of the data. Pseudo sections for some simple objects. So here's one in which we've got just a conductive block in a half space. You know, pseudo sections kind of got this sort of pant leg thing on here. So this is low resistivity. So if you didn't know anything else, you might think, oh, maybe drilling someplace in here might be good. But it doesn't take much to really screw up things. So if I put some conductive blocks up here, then my pseudosection now looks like that. So now you can't make any sense out of just looking at the pseudosection plot. And here's one in which we've got kind of a variable conductive overburden. We've got two blocks in here that are conductive, but the pseudosection looks like this. It was tempting many years ago to, for people to look at the pseudosection and say, oh, well, I've got this great big conductor down here. Let's just drill down through here. Well, if you've done that, you've gone right between these two guys. So that means, of course, that you need to invert the data, and we're going to use the same kind of process. And here's what happens when you do that. Here is our block. Here's the pseudosection, and now you invert that, and you get this. So it's not too bad. It's sort of centrally located, same as this. It's kind of smoothed, but that's because of the regularization that we used in our inversion. We asked for some algorithm, so that's pretty successful. I think this one's kind of interesting because here is your pseudosection, and it's really mucked up, but you invert it and you get the blob, but you actually also get some of this other stuff up here, right? So there is actually real honest to goodness information about the near surface as well as the deep thing. You simply don't see any reflection of that body in the deep pseudosection. So the pseudosection, again, is a way to plot the data. Do not make geologic interpretations from those pseudosections. And here we are back here with this double model. Invert that. Clearly you got two blocks. You're good to go. So the world, so that was like 1D and 2D. World's 3D. And that really does make things complex. We've got variable hosts, we've got bodies that have different geometry. So then you're actually in some kind of serious questions. Is like, okay, where should I put the currents, right? Should my acquisition strategy be 2D, 3D? Where should I make the measurements? Which measurements do I want to take? What's the effect of topography? Yeah, these are all questions of survey design. But the crucial element here, and we can kind of bring it down to that, is basically sensitivity. So if I was asked somebody to give a definition of sensitivity, especially within the context of an inverse problem, because that's what we're trying to do, anybody care to offer just a generic definition? Yes? Let's see, so who's sitting beside Stephanie?
Jonas.
Jonas?
Yeah.
Okay. If somebody says sensitivity, what's the kind of thing that, yeah?
Loud changes in the apparent values for little changes of the setup. Right? Yeah,
that's good. That's good enough. So when you talk about sensitivity, you're kind of talking about, okay, if I change something down here, so maybe I change a geometry or maybe change a physical property value, what does it do to my data? Right? Am I sensitive to that? That all is part of survey design, right? Because you're trying to design a survey that is sort of sensitive to that. So here's, I think, what most people would think, that the sensitivity is really, like if I change the, some parameter in the model, let's call it P. So if I change that a little bit, might be a shade, might be a value, then what's the change in the data? Okay, so that's a way of kind of thinking about sensitivity. If this number is large, that means small change in the data is, you know, or small change in parameters, a large change in data. So that's good news, right? It means I'm sensitive to that. To collect data that are sensitive to a target, it's actually useful to divide it into two parts. If people just start talking, you know, if you're in the process of survey design and you're thinking about, okay, I'm going to develop the survey design or survey, and do I have good sensitivity to this target? It turns out that that's actually a complicated thing to do. But if you split it out, if you break it down into two parts and think about each of them independently, so you don't think about sensitivity all at once, but rather you break it into two parts. And the first part is to excite the target. We somehow need to make sure if we've got something down there, we've got a transmitter, we need to excite that target. And the second thing is, once we've excited that target, we've got an idea of like, okay, where should I put my instrument, or what field should I measure? But there's actually two distinct things there that are useful to think about in concert. So if we come back to our sphere here, so we've got our currents going through our sphere, and if we look at our charges that are built up, we're actually good, right? We got a big set of charges on that sphere. So I've really ignited that thing, and I've got correspondingly good secondary fields, and I've got good potentials, right? So that was this was a good place to put those currents to excite the body. Good to go. What about the measurements? Well, the measurements, you can see they're almost intuitive, right? You somehow want to be as close to this body as you possibly can, and get these electrodes close to those negative charges and close to the positive charges. And so depending upon where you are with respect to that, you've got different relative orientations between those charges and the potentials, and that tells you what you're going to see. But the thing that's kind of nice about this is that the excitation fixes the charges, okay? And now you come along with some kind of a device to measure things, and now you can see, at certain points I'm going to be really sensitive to this thing, at other points not, right? Just enriches your information about what's going on. Another thing that we haven't talked about yet, we had a sphere, but we've got issues of what's called coupling. So that is relating kind of what our primary fields were to our object. So for instance, suppose that we've got a plate this way. So we've got an A electrode B. We've got a plate that's this way. Then how are the currents going to be distorted? Well, I've got to kind of get sucked in a little bit here, get sucked out there, and basically go like that. If I lay the plate the other way, now I've got currents that look like this. So certainly in these two cases, the charge buildups on those two plates is going to be very different. So I'm going to expect that I'm going to have somewhat different results coming out of these, just depending upon the coupling, what the orientation of the plate is. And then the other thing is, so I've talked about coupling, but what's the differences if I've got a resistive target or a conductive target? Does it make any difference? Wouldn't expect very much, whatever, right? So if I now do that, if I have a conductive target, so keep coupling the same, I got currents that are flowing in through here. So I got negative currents, positive current or charges here, right? So that's my excitation from here. So I've got negative, positive, and moderate size. Look what happens when I make this a resistor. Okay, now the currents can't go through a resistor, right? So they go, sort of around like this. And now if I look at my charges, first of all, you notice that the charges have changed sign because I'm now going from a conductive to a resistive body, so that flips everything up. And I've got these big red charges on this side and the big blue charges on that side. So I'm really changing what's going on. So a conductor and a resistor are going to behave very differently when I'm trying to excite them with a galvanic source. And we're going to see that kind of coming through a little bit more as we progress on. So in summary, our sensitivity, we need to drive currents into the target. We need to get good coupling. To measure a datum, we need to try to get that potential electrode as close as we can to all those charges. And the other thing is that the background resistivity is also going to be important. So now we come back to these questions of survey design. Okay, so you have to ask yourself, first of all, what's the objective? Is it a layered earth? In which case, I could do, if it's 1D, I could do sound, no problem. If it's 2D, I got to do a profile sounding and kind of go perpendicular to the geology. So the geology is going this way, then I just want to go across that way. Note something, if it's 3D, then you somehow need to have 3D coverage. And in order to do that, yeah, you just need to know a lot of things about the background of the resistivity, noise structures, power lines. People had mentioned there's a lot of electromagnetic noise there. But in general, frankly, this is kind of where we're at. There's just too many variables, and you just have to resort to numerical modeling. So suppose that we're in a case where we've got sort of a general background geology, and there's a couple of features that are coming in here. These are the target bodies that we're looking for. I mean, what do you do? So you define your general geologic model, you assign physical properties to it, select the survey, and then you simulate like with the target, which would be the red line, and without the target, which is the blue line. And then you look at the difference. And the important point from the point of view of assessing the difference is two things. One is that this value here should be greater than some floor value, some overall sensitivity of your instruments and whatever, and also generally has to be greater than some kind of a percentage. Usually kind of need to be brought into practice just to make sure that your signal that you've got here is actually going to be meaningful when you've done that survey. And in fact, the same reasons kind of come back in when you're faced with any data set, okay, and then you have to assign uncertainties, which is one of the big problems in inversion, in practical inversion, is, okay, what rule do I use? Generally, some aspect of a floor and a percentage is a pretty good place to start. So, yeah, I'd like to do a quick case history. We're going to be about just another 10 minutes to finish up the case history. So it'll be a little bit late on lunch here, but I'd like to show you this. So the place is Mount Isa. So it's a mineral exploration project. It was done in the northern part of Australia. And we're going to parse through this in terms of our 7-step procedure. So the first of it is the setup. What's our geologic model and where are we? So the geologic model, it really doesn't matter what these things are. They're different. They're different colors. They're different units. There's a couple of guys that are really important. One, this red triangle in here indicates what's called a breakaway shale. It's a very highly conductive object that it's not interesting from a mineralization perspective. And then there's mineralized zones that could be in other various units here. The real question is, can conductive units, which would be potential targets within the siltstones, be identified with DC data? Okay, so we're going to try to say, okay, is a DC resistivity experiment going to be useful over here? The geology is predominantly running north-south, so we could actually think about using, that profiling sounding technique and just collect data along a bunch of lines. So first of all, what's our properties? Well, these different colors here have different rock units, and they've got different conductivities. The important thing here that we're looking at is conductivity, and there's two things here. One is the Mount Novot horizon. That's what we're looking for. He's mineralized, and we'd like very much to find him. He's got a high conductivity. And that high conductivity is much greater than these volcanics or some of the siltstones. And this Mount Novot horizon is hosted in those siltstones. Okay, so the very first thing with trying to make geophysics useful is that it has to be different. The thing you're looking at has to be different than the surroundings. Okay, so by and large it does that, except that there is this other unit out here called this breakaway shale, which has a very high conductivity. So we're going to have to kind of contend with that. So what's the survey and the data? Well, we're going to do east-west lines of data, and there's really not very much for surface topography. We're going to have a pole dipole, so we kind of introduced that. So we've got a current pole, and then we're going to measure the potentials. So we put the current here, and then we just measure the potentials all along here. Then we move the current dot, and we gradually build up this pseudosection. The red on this pseudosection is high conductivity. So there's something happening, right? Like it's red on these 10 guys that are going there. So that's that's something. Lots of the data, at least it's showing you something. Remember I talked about excitation? And it's no good always maybe just to excite from one side. Maybe we want to excite from another side. So we could just flip this guy around, and we could use a dipole pole. So now my current pole is on this side, and the dipoles are here. And now you notice it's a lot different, right? I mean, it's still got red over on this side, but these are, it's really much bigger in there. Okay, so there's your data plots. What do they tell you about the geology? I mean, they really don't tell you very much, right? So you need absolutely to unravel these through an inversion, which is what's going to be done next. Okay, so now what we do is we take these data, it's over a volume, and we're going to divide our volume up into a whole bunch of cells. In this case, it was about 500,000, I guess. Actually, I must say I'm extremely proud of this particular example because it was, I believe, the first example of 3D inversion for DC data being done on a mineral exploration project. We did this back in very late, well, I guess it was very early 1990s to do this. So this was one of the first things. This was absolutely state of the art at that time. And I just like to kind of show it because A, we had done it, and B, it still actually is a very useful example. So what we're going to look at here is the output of the inversion that is all in conductivities. The red is going to be conductive, blue is resistive, and we're going to look at it in various ways. We're going to sweep back and forth here, and then look to see what cross sections are. We're going to look at plan views, and then we're going to rotate it around and to see and change the isosurface value, and then see what we're left with. Nice. Okay, so we're sweeping back in. So you can see this great big red guy on the right-hand side. We'll come back out. Just go down. And now we're rotating around. And as we rotate, we change the isosurface value. And there we're left with. So that's our final model. So geologically, now we've unraveled geologically what's happening, right? There's just this. The first order is that there's this great big conductive linear feature that's running through here. That's going to turn out to be a black shale. There's also, you know, more of a conductor here. If we plot it up in a color scale, it looks like that. So what's our interpretation is that this guy here is this black shale unit. There was a hint of a conductor that we saw sitting up here, and if we actually looked at the movie a couple more times, you'd see that, you know, there's various manifestations of something that's highly conductive. So that is a potential for being that mineralized zone at this point. But we really can't tell that from just the resistivity section. In order to really fully do that, to fully get this, we're actually going to have to recognize, like, oh, wait a minute, there's an IP signature for this rock unit. And then we're going to close out the day by looking at this same example, but looking at the IP data over there, and then finding something that's high conductivity and high IP will delineate this. So this is kind of like the first half of that. Yes. Okay, so there's a case history. We're going to, if people are interested, we could go through a case history. It has to do, it's by Bolev, I'm not sure if I pronounced that correctly, and Revel, 2009, where they have an embankment dam in France, and they use self-potentials. Anyway, we could talk about that later. I just want to show you, I want to conclude with one thing here before lunch or before coffee. And that is this guy. Okay, so here, just to quickly wrap up, so we've kind of done some introductory stuff, and then we've looked at one case history. The one thing we haven't talked about that's very important is the effect of background resistivity. So we did this example, right? So we've got a sphere, conductive sphere in here, and we see that if we have currents going like this, that we ignite that guy. So my question now is, suppose that I've got a background that's more complicated than just a homogeneous half space. So suppose that I put in a thin layer up there that has got a very high resistivity. Okay, so I'm going to take this, make a layer, high resistivity, do the same experiment. What's going to happen? Somebody?
Horizontally or vertically?
Oh, sorry, horizontally. It's going to be a horizontal plate that just goes above here.
Then the apparent resistivity increases, but not too much compared to vertical plate.
Okay, anybody else? Is it going to affect my ability to see the sphere? Okay, in what way?
Less current is going to flow there because it's flowing in the upper layer where the resistivity is low, or the conductivity is higher. And the current will flow in the upper layer and not penetrate this deep.
Perfect. Okay, so if we I'm not sure if you can see that. It's a little bit dim. So I've got, here's my layer here. I make it really resistive. And when I do that, by resistivity, it's high resistivity. I can't drive current through. So the current is forced to stay up top. So the current just goes through there, and I simply don't see, I do not see the sphere at all. I do see an elevated resistivity, so that you were correct, 1,652 ohm meters. Right? But that resistivity is caused only by this resistive layer here. If I do the same experiment, take away the conductive sphere, I don't change anything. So this is a very important point. When you're using DC resistivity and you've got even a very thin layer that is highly resistive, you can be completely hooped. And okay, so that's the resistive layer. What happens if I make it a conductive layer? Anybody? Conductive layer?
Depends on the contrast between the background and the layer. But the current is not so motivated to penetrate deeper again because it can stay in the conductive layer.
Perfect. So if we have a conductive layer, so now I've put a 1 ohm meter layer there. Now all the current is actually in the conductor. When it was a resistor, all the current is kind of uniformly distributed up above the resistor. But now, and notice how it dropped down? So everything is in the conductor. And again, so now my apparent resistivity is 47 ohm meters. So it's like, oh, it's low compared to 500. But if I did the same simulation without sphere, I get 47 ohm meters. So DC resistivity, it's good, got a lot of potential. If you have extreme background host resistive units or conductive units, you could be challenged. So what we're going to do next, what I'm going to do is we'll start to use inductive sources and then see, okay, we're going to come back and look at these same examples. Now we have an inductive source. How is that going to be effective? And then see if we can see that sphere beneath that resistive layer or maybe beneath the conductive layer. So that is where we're going to go next. So here we are, a few minutes behind, but I'll have coffee and then return in, I don't know, 15 minutes or something like that. We could probably, since we're going from 9 to 6, right? So we could maybe have lunch at like 12:30-ish or something. That would work. Is that?
Sure.
Okay. Let's do it. It's okay. It's fine. Oh, I just wanted to know.
What about the fibers? Is this the same service within short-term office? And the example?
Yeah.
Of monkeys?
Yeah.
My master's student said that there were 8 servers, then we have just 2 stations. So I guess
No, yeah, there's 10.
Das war eigentlich alles, was jetzt hier das Problem ist. Da scheint irgendwo ein Problem sein, weil es unten von der Box nicht kommt.
Wer hat denn das Kabel da oben angeschlossen?
Weiß ich nicht. Also es war
Das war so, wie sie kam?
Ja, so kann man bei Renter war das vielleicht.
Das ist natürlich so ein bisschen unschön.
Ja.
Ja gut, das HDMI-Kabel ist ja auch ausgestellt, ne? Das liegt ja daneben. Gucken wir mal, ob da was... Wo laufen wir denn hin? Können wir wieder nicht gucken. Ne? Das ist jetzt so wirklich die Frage, weil... In den Bodentank.
Ja, ob man meint, vielleicht kann man das jetzt sagen.
Sie bräuchten jetzt das HDMI-Kabel, ja, oder?
Nee, das funktioniert mit dem jetzt eigentlich auch. So, wir bräuchten eigentlich nur ein Mikrofon.
Ja, das müsste eigentlich dann im Raum.
Achso, da hat er ja.
Genau. Probieren wir das mal gerade raus.
Wir wollten diese Mikros nutzen.
Ja.
Und die funktionieren nicht. Das war, glaube ich, das.
Ja. Kannst du mal sagen?
Muted ist er nicht.
Trying to keep that outside region just more or less. Not very.
Ja, dann kann ich's.
And we're able to show that, yeah, most of that.
Ich guck mal gerade nach dem Empfänger.
Those interesting, yes. Yeah, it's always a question. Okay. But you do want to generally have a volume that's much larger than your surface. Because you also have boundary conditions.
Especially for the geological interpretation, I find very hard to decide how trustworthy the pictures are.
Yeah.
Exactly like you mentioned, when you have something that just at the sensitivity boundary, it's like,
yeah,
what's going on there?
Yeah, so I think one of the ways that one can work with that is just to do some adjustments and some further inversions. Just try to see, okay, that's the feature. Can I generate something that doesn't have that feature? Or can I, whatever other question you might want to ask it.
Once you receive your starting geological model, is by seismic or?
No, which is homogeneous aspect.
Okay.
Yeah, sorry, there was no other a priori information.
No.
That's actually going on.
Irgendwas kommt aber, ne?
Klingt gut, aber es kommt nichts durch. Kapseln über.
1,16, dann gucke ich mal gerade hinten. Ja. Multimedia-Raum, ich glaube, das ist der Nachbarraum.
Ja, nicht, dass es drüben spricht.
Da steckt noch eins mit Besprechungsraum. Da wird wahrscheinlich eh keiner drin sein nebenan.
Nee, glaube ich auch nicht, aber ja, das wie gesagt, ich weiß
Ich
ja,
muss mal gerade den Hagen anrufen,
dann,
ob der
weiß
weiß.
nicht, wer das gemacht hat.
Das,
Ich meine, da muss ja im Grunde auch beklettert sein. Ne?
ja, vor allem sind diese Kästen eigentlich abgeschlossen, dass man da gar nicht drankommt.
Ah, okay.
Du kannst eigentlich nur einmal Kabelpool und hier hinstellen,
Die ist richtig, ja.
Man sagt eine Frage in das Raum, ne? Berlin, weißt du, dass der untereinander? Weil die hängen vom Käfig, der ist jetzt offen, und 10 Meter VGA-Kabel runter, einfach nicht. Und dann haben wir alles ausgestreckt. Keine Ahnung, ich lasse das jetzt auch mal so, aber so kann es ja nicht sein. Ne? Ich habe auch keinen Leiter, deswegen kann ich nicht rankommen. Der Käfig ist doch nochmal auch abgeschlossen. Ja. Ja, aber der sagte doch damals auch, der hatte keinen Schlüssel dafür. Ja, kann ich mal gucken, ob der da ist, aber wie gesagt. Ja, das war ich. Ja, also der war ja auch gerade schnell drauf. Ja, jo. Sollst du mal, wenn das Ding am Ausgeht, überraschen? Ja? Ja, ausgeschrieben. Ich weiß ja immer.
Wir müssen in der Pause stehen. Steht Pause. Ich will auch aber sonst alles nur Essen aus dem Pause. Ja, okay, wir müssen es.
Und tut eins bei den beiden oder? Nicht. Ja. Also die Mikrofone genau. Ach so, okay. Das dahinter. Perfekt. Also liegt tatsächlich in der Anlage. Aber es ist auch ein Ding, dass das eben gemeldet wird. Dann muss er hier. Ich wusste nämlich auch gar nicht, dass der abgeschlossen ist.
Der schickt schon mal mehr. Wir haben das mal gesehen.
Ja, kann schon mal.
Ja, aber da muss er wirklich einmal.
Ja, dann machen wir mal den Herrn Voss, der sitzt hier unten. Genau, vielleicht. Der kriegt dann nochmal ganz.
Aber das heißt, jetzt können wir eigentlich jetzt mit dem machen, was ich weitergehen.
Und dann ist da tatsächlich keine Alternative. Das ist der Verstärker und der Film von einem Produkt. Dann schon mal richtig. Hat ja auch eine Größe. Vielleicht weil wir auch irgendwas benutzen. Weil ich weiß nicht, man ist noch von anderen Produkten gegangen. Das wird ja auch kosten, die ja, wir brauchen die Menschen von der Seite gehen, man ist die verwalten Geo tatsächlich mit. Also wenn man was austauschen, das auch wieder aus oder Region, diese zwei Räume, die sind halt einfach nicht von uns verwaltet. Ja, jeweils was da produziert, das auch
Das heißt, dass dann Sachen bestellen oder die zerstellen Sie den Rechner?
Problem an ist zum Beispiel letztes Jahr auf jeden Fall ich weiß nicht, ob der jetzt aktuell immer noch so kleiner Beamer auf dem Plattform steht. Ich kann immer Spaß angucken.
Und wie läuft das dann, das Prozedere? Der Herr Voss sagt Ihnen Bescheid und Sie schicken dann Rechner.
Genau, entweder wird das dann über uns bestellt, dass er die Rechnung kriegt. Das Problem ist, dass er die Rechnung Sachen wie auch vorne, dass das Display anscheinend irgendwie Macke, das schaltet ja immer zwischen den Winkeln hin und her. Das ist ein relativ schwierige Angelegenheit, so weit kann er eben nicht rauskommen. Ja, das macht dann die Firma tatsächlich, die es eingebaut hat. Wahrscheinlich wird dann auch jetzt ein Kabel da dran und es funktioniert das nicht mehr. Ich guck mal, war das Spaß gegen andere?
Keine Ahnung, erstmal muss man es ja jetzt feststellen, kommunizieren, und dann muss man ja immer abgeben. Also Freitag habe ich mich auch nicht getraut, dann war ich von der anderen Seite und da war er nicht mehr. Also da konnte man.
Das ist der Computer. Das ist der Computer. Ja. Diesen Raum hier muss ich bei den Geografen. Diesen Raum habe ich so mit der Geografie gehauen, genau, das war am Jahr gelernt. Aber ich habe
So just make sure that I just use as here or. So here I can get rid of that. And
Yeah, I was going to kill your Skype when your Skype is running. Because that makes a noise when people sign on.
Get rid of that.
So it's actually the overall system. They cannot fix it.
Okay.
So we have to actually continue.
Okay, that's fine. We can do that.
Okay, so
yeah, and start
back
to
in, right?
corral them in.
Do you want some more hot water?
No, it's fine. I'll just use cold.
See what's going on in your background.
Why does it take you so long to boot up?
Can you scroll to the top?
Oh, there you go.
Should be good now. Yeah, if you just make this big, that'll give you a little more space to, and then you can do command minus.
Yeah.
I have no idea.
So, one of the I think major achievements of the of the whole group at UBC and others are also now starting to kind of get on board is the development of apps that allow you to kind of explore things, ask questions, visualize things. These are they're tremendous learning tools, and we've now got, I don't know, about 25 of these available. Lindsay will take you on a run through tomorrow on how you can not only access them, but see what's behind, how they're developed, and maybe motivate you to develop some new ones. And especially in the world of electromagnetics, there's always so many little things that you just kind of come across and you're like, well, I'm not really sure about that, right? And if you've got something that you can work with, that you can ask a question of and get some result out, then you're kind of good to go. So I'm going to show you one app. It's a DC resistivity app, and basically it looks like this. You're going to have a functionality to have an A and a B electrode. You can put them anywhere. And an electrode, you can put them anywhere. And you've got a background, and you've got some kind of a target. Put this into context. One of the questions that's invariably asked to me, and I think for any geophysicist, it's certainly any applied geophysicist, this is the kind of question that people would ask, and they would they come up and say, can you use DC resistivity to find a tunnel? Well, think about that question, okay? If I asked you, let me ask you, okay, can you use DC resistivity to find a tunnel? Steph, what do you say?
How deep is the tunnel?
Good. That's exactly right. Okay, so you need to, there's one question. What else might you want to know?
How big is the tunnel?
How is the dimension of the tunnel? Like, we're talking about like 10 centimeters, panels, or like 20 meters.
Yeah. So you need to know about the geometry, because you already know that, okay, for certain sizes tunnels you might be able to get them, but there's another important question about the tunnel. What's that?
Resistivity of the tunnel.
Yeah, resistivity of the tunnel and the background. Okay, so let's there's certain level of questions that just can't be answered because there's not enough that is explicit. But let us. I'll just quickly show you. So here's the slider bars. You know, A, B, M, N. Here's the radius of the tunnel. This is the center of the X location of the center of the tunnel. This is the Z. And 1, that's the background resistivity. And here's row 2, the background or the resistivity of the tunnel. And then you can, we'll come back to that in a second. So first of all, let's build a tunnel. What do you want to start with? How about the radius of the tunnel? 10 meters. Okay, that's currently what it's at. Don't even have to change the slider bar. Whoa, you're making life easy. How deep should it be?
1 kilometer.
Oh. Sorry, our scale doesn't go that far. But you know, interestingly enough, that's what a lot of people want you to do, right? Yeah. Pardon me?
There are tunnels.
Right. We have a horizontal limitation here from -40 to 40 meters. So we can put our current electrodes within that space. Kilometer deep is a little bit big. Anybody? -20 meters. Okay. So that's also a little bit. You guys are not very creative. Do better. Okay, so there it is. Right now we don't really see anything, right? And the reason for that is that we haven't changed the resistivity of the tunnel. So what kind of what's in the tunnel and what resistivity should we make?
5,000.
Pardon me?
5,000.
5,000. Okay. And our background? 120. 0.576. Right? Very German. Okay. 120. Okay, so we've got a fairly conductive background, but very resistive object, and where's my tunnel? What happened to my tunnel?
Here's rerun the cell. I'll rerun the third one.
And this one?
Yeah. Okay. If not, I'll pull it up locally.
Huh.
No, you don't need to rerun that one. Yeah. Do you want that? We can run it locally.
So these, right now it's all set up that it's running in a Microsoft Cloud, Azure, which means that you don't have to download anything, but for some reason or other, I decided not to do that. Yeah. So anyway, what we're going to explore is we'll make our tunnel, just get an idea of the flexibility of what you can plot and look at without actually going through a lot of stuff. So what we had, row 1 was 120, and we had 5,000. That's better. Okay. So there you go. We got a pretty substantial tunnel. It's buried. The depth of it is 20 meters. And if you look to see what the electric potential is, you see that the potential is infinite at the A electrode and infinite negative at the B electrode, and the difference between the green and the dashed underline line, if you can see it, is the difference with and without the body. Okay, so that's where we are. But the things that you might want to look at, actually, what would you like to look at? Any ideas? We could look at the potential. We could look at an electric field. We could look at currents. Currents are always interesting. Anybody? Anybody? Okay. Let's look at currents. Okay. So in this case now, you can see that the currents are being deflected around the object. We've got a very high resistive contrast here. So that's what the currents are, and there's changes in the electric potential because of that. Okay, so that's interesting. The other thing I talked about was, well, so here's the total currents. If we looked at the primary currents, so we talk about primary currents, then those are the currents without the body there. So that's the natural state. And if we look at the secondary currents, that's the currents that are the difference between the total and those, right? So you can see that here, those currents are, it's just kind of acting like dipoles that are sitting. So you kind of have an electric dipole. Okay, so I talked a lot about charges. So what about charges? So on this field line here, we can also look. So we have electric field, we got charges, and total charge. So the total charge, what are we expecting? That's what we get. So I look at all of, I've been talking about all those charges, but now I actually compute the charges here, and I get something that looks like that. What's going on? Anybody? Well, everything's kind of white down here, but there's a couple of dots here at the current electrodes. And that's where really all of the charges are. I mean, what happens? I mean, you imagine like you just basically take a battery and you hook one, a positive probe up. I mean, it's like, okay, that's just like a big charge that's there. And so really you've got a big charge, positive charge here, and a negative charge there. So that's the primary charges. So let's now look at the secondary. And they become much more like we would anticipate, right? So now we've got current or charges here and charges here, and our apparent resistivities with this configuration is 157. So I'm measuring this potential difference, and I've got a reduced voltage gives me an apparent resistivity 157, which is larger than the 120. Okay, so I'm actually seeing some effect of that of that sphere. So it's not 5,000, but it's definitely larger than 120. So you can do some interesting things with this. I don't want to, it's easy to spend a lot of time. We don't want to do that. I'm going to just do one thing that's kind of interesting, and that is I'm going to work with a pole-pole system. So I do that. So the only electrodes that are activated are the A electrode and the M electrode. And I'm going to put that M electrode close to the A. So now what we see is so here's the potential that I'm going to get out with this system. So here's our potential electrode. And you can see that this potential electrode is closest to these positive charges here, and that my apparent resistivity is 134. Okay, so that's good. Everything is kind of consistent. The only thing I want to do now is I'm going to move this potential electrode. Okay, I got to put it up here, and I want you to watch what happens to the apparent resistivity, and that will then fix that conundrum that we had earlier. So I'm going to move this potential electrode, first of all, here. So now it's sitting right here. And, you know, it's still a little bit larger than 120. Because these charges here are positive, and they're actually bigger than these, even though I'm a little bit closer to these negative charges. But if I go out farther, there we go, 116. So it's undershot the background resistivity. So the apparent resistivity 116. And that is really just simply because I'm actually closest to these negative charges. Okay, so that's just by now kind of understanding that relationship between, okay, the charges and the voltages, the measured potentials I'm going to see, you can start to understand a little bit more about, you know, why I got that overshoot in, you know, especially in that profiling mode. It was over quite a bit, right? The other thing, I'll do one more thing here, that's kind of interesting. I'm going to adjust, maybe I can make it a bit smaller. Yeah. I'm going to stick with pole-pole. Okay, watch the charges. Okay, so I've got positive charges here, and now if I'm going to move that A electrode, yeah, see? So you can see how the charges are moving with respect to that, right? So that's the excitation part, right? I got a current here, and now I'm moving that over, and those charges are just kind of rotating with that current system. Good. One last thing is, instead of having it as a resistor, I'm now going to make it a conductor, and now you can see how I've changed the sign. I'm going from resistive to conductive, so I get a negative charge and then a positive charge on the X grid. And now watch this guy as we rotate back. All right. Good. So that's the basics. There's an app. Actually, there's a number of apps with respect to DC resistivity, and yeah, you're encouraged to explore. Okay, so let's now. So, any questions about that? in Bonn. We've done DC. Oh, dear me, it's 11:30. O'clock? No, I wouldn't do that to you. 7:30 is the latest. Can't talk me into anything larger than 7:30. Okay, so now we're going to flip gears. Now we're actually going to go to electromagnetic induction. So we're going to first look at things like Ampere and Faraday's law. We're going to introduce a two-coil system, and then we'll look at frequency and time, do a sphere and homogeneous Earth, and talk about energy losses in the ground. So the basic experiment for EM, we've got a transmitter and a receiver. In this case, you're going to be towed in a bird. So here's a transmitter, here's a receiver. So the transmitter gives out a time-varying magnetic field that goes everywhere. That time-varying field induces currents inside this body. Those currents give rise to their own magnetic fields that could be recorded at the receiver. So that's basically the steps. What I'd like to do now is to kind of go through, make sure that we've kind of got all of the understanding of what's going on, and taking a little bit closer look at various elements. So first of all, the transmitter could be time, could be frequency, and it's generally a little loop of wire in here, a little coil, and that's going to give out a, this time-varying magnetic field. Our equations, these are called quasi-static equations because I'm going to omit one particular term, and that is the displacement current term, this guy here. So we're basically operating at a frequency that's much lower than what you'd work with for a GPR. We're going for here everything from basically DC for most practical applications, maybe 100,000 hertz, certainly 10. And so those are the equations we want to solve with our sources and boundary conditions. So let's just first of all look at Ampere's law. So we said curl H is equal to J. And for this, you're all very familiar with. You remember, I got a current in a wire, so I'm going to put my thumb in the direction of the current. Rotation of my fingers takes me the magnetic field. So it looks like that. Depends upon magnetic field strength, depends upon the current that's in there. If we take that loop or that wire and we roll it back in on itself so that we have a loop, then we get a magnetic field that looks like this. It's effectively the field of a bar magnet. And it's got an expression like this. The important thing is that it depends upon a strength, a magnetic moment, which is equal to the product of the current times the area of the loop. And it falls off as 1 upon r cubed. So it has that shape, falls off as 1 over r cubed, and linearly depends upon the dipole moment. So Faraday's law is given by this. It says a time-varying magnetic flux creates an electric field, a circular electric field, and there's a minus sign in here that was due to Lenz. And so we couple that in with this constitutive equation, which is J is equal to sigma E. And again, I think everybody's very familiar with this, especially in this audience. And that is if we have a circuit that looks like this, so it's got a coil, it's hooked up to a light bulb and measures the voltage and makes a complete circuit like this. The idea is that when we have this in a steady state format, so imagine that we've got a bar magnet that's just sitting here. The thing that's important is the flux, the magnetic flux is the integral over a particular surface of B, flux density dot n hat dA. So it's the amount of magnetic flux that's coming in through here, and that is evaluatable. And what's really interesting and important is that it's the time rate of change of this which gives rise to an induced voltage in a circuit. So here's our circuit. We've got current going through here and represented by resistor and inductor, and we're going to get a voltage that is induced in here depending upon that time rate of change. If we move the magnet in, then the flux increases, time rate of change is with the negative sign is actually less than 0. So that means that the current goes in one direction, but it's still lighting the bulb. If we do the other way, then we still have a change in flux. Now the current is going to be going in the opposite direction, but the bulb's still lit up. And yeah, we end up in this situation. So there's a couple of apps for Faraday's law. They're both built on this sort of simple geometry where we've got a primary loop that's in here. So the current in here is I sub P, which is primary. And there's an inner loop here, which is a target loop. And that target is represented or is characterized by a resistance R and a self-inductance L. So, as I said, two apps, one's for the harmonic, one's for the transient. So let's just look at what's going to happen for our two-coil system if we have a time turn-up, if we have a transient. So the primary current looks like this, so it's on, then it gets turned off, and then it's 0. Magnetic flux looks like this, just follows the current, goes off. The time variation of that magnetic flux is just a delta function, and then that change of flux onto the coil here, onto the target, induces those currents in here, and those currents are going to decay away. So here's our circuit. The current, secondary currents as a function of time given by some magnitude e to the minus t upon tau. Tau is a time constant. Tells us how quickly everything decays away, and it's dependent upon this ratio of L upon R. If you ever want to make money on the side, just develop, a cough drop machine that can sell lots of cough drops. I'll be a good purchaser. You can make lots of money. And if you make a lot of money doing that, I'll tell you about a new recipe that we invented for making pesto using carrot tops. Trust me. Sorry. Here we go. We're on geophysics, right? There we go. Okay, so we have this magnetic field comes in, we turn it off, it's generating currents in here. They're going to fall off as exponential with a time constant. So we actually call that a response function, this e to the minus t upon tau. It tells us how the fields are decaying. If we plot that in a log linear plot, looks like this. We just take the log of that. If we plot it as a linear plot, we just have these decaying exponentials. So response functions for time domain system or the coil really easy. What happens if we have a harmonic? Well, the difference here for transient pulse is that there's no primary field in here. We always have a primary field. So let's just think about that a bit, because this is actually one of the things that for people who don't really understand electromagnetics, it's one of the things that constantly get tripped up on. But in fact, it's actually very straightforward. And I think this app that we developed kind of helps that. So first of all, you can imagine a primary current that's going in here, but it's harmonic. So if we look at the primary field current, it's in red. So it goes like this, right? So it's working at a particular frequency. If that's varying in time, so there's an induction effect that's going to happen in here. So there's going to be currents that are going in here. And first of all, those currents have to have the same frequency, right? There's only one frequency happening, so the currents, the secondary currents in the loop have to have the same frequency. So what can change? Well, they could have an amplitude that is different from the primary, and they could also be phase shifted. So we could take this green curve here, and we could decompose it into two parts. We could have a part that is in phase with the with this primary current. In other words, my primary current's going like this, and my secondary current's kind of following along the same, right? And then we have a part that's out of phase. So the primary current's going, primary current's going like this, right? And the other guy is kind of going like this, right? That's it. We're just decomposing it into two parts. And if we add this and this, we get this. So that's the only thing that we've done is we've taken the sinusoid and we've just decomposed it into two parts, one which is in phase and what is out of phase. And mathematically, you can do that very easily because the secondary field is still going to be like a cosine omega t, but it's got a phase shift in here. And then we decompose this guy into the sum here. So now we've got a part that's developing as cosine omega t and a part that's sine. And then whatever coefficient that we've got out of here is that part of the data. So in here, and here again is where some of the confusion comes in because geophysicists, and certainly me, like sometimes I'll talk about this as being the real part. Sometimes I'll talk about the in phase. It's the same. It's just different words. And out here, it's like, oh, the out of phase, or the quadrature, or the imaginary. We're sloppy. We use all three of those, but they all mean the same thing. The phase lag has got an expression that's given by this. So you can see it depends upon this product of omega L upon R. And that guy is called the induction number. So it doesn't matter what these numbers are individually. If you make them so that they have the same product, then you're going to get out the same phase shift. So everything kind of depends upon this thing called the induction number. If we plot that quantity, we can get with the response function for the frequency domain looks something like this. The in phase is this black line, kind of goes up like this. So we've got induction number here against the response. Okay, so the in phase looks like that. The quadrature phase looks like this dashed line here. So that's a classic picture. You'll see this in every electromagnetic book that you look at. And there's a lot of information in here that tells you a lot of useful things. So it's kind of important to understand where this guy is coming from. So in summary, we have a step off or a harmonic. Doesn't matter. For both of them, there's induced currents given by these equations here. They generate secondary magnetic fields. And they're the same. The only difference is that here there's a primary field that's constantly in the picture. Okay, so that gives us those induced currents. Now, by Ampere's law, we want to, it gives us a magnetic field. And so we're going to measure something to do associated with that. It could either be the magnetic field itself as a function of time. So we could measure 3 components. Let's suppose we had a flux gate magnetometer, would work. Or we could measure dB dt with a coil system, so that we're really measuring a voltage. If we're measuring these voltages with the coil, then each coil orientation only measures like 1 component. So if we wanted to have 3 components, then we need to have 3 coils. And so coupling matters, and we're going to talk about that in a second. In fact, we're going to talk about it right now. So what we mean by coupling for these kind of loop systems is, well, the flux from a transmitter is going through, let's say, the coil representing the receiver. In this case here, you see you've got basically perfect coupling. The field is coming straight down through here. If we look at the coil orientation here, there's actually no flux that's going through that coil. All the magnetic flux is going parallel to the coil. There's nothing that's crossing its surface. So we call that null coupling. So that's perfectly well coupled. It's null coupled. This guy here is kind of moderately coupled. The coupling comes about in 2 places. It comes about first in the transmitter to the target. So that's kind of like a 2-coil system. But there also comes about from the fields from the target to a receiver. Right? So there's 2 kinds of places where coupling comes in. So now we're in a position to put it all together. So first of all, we've got what we consider to be our sort of real situation. We've got a transmitter, we've got some conductor down here that we're looking at in a receiver. And we have primary fields that go from the transmitter to the receiver. We've got fields that go to the conductor, and then fields that go from the conductor back to the receiver. We represent that in terms of a 3-coil system. Again, this is completely iconic. I think if you look at really fairly old textbooks like Grant and West, I mean, you'll see these things laid out very, very nicely. And so we got a loop to represent the transmitter, a loop to represent the conductor, and another loop to represent the receiver. The coupling here for any of these just depends upon the relative geometry. So the coupling between 1 and 2 depends on just this geometric quantity here that's given. And so we'll have M12 being the coupling between M1 and M2, M23 the coupling between here and here, M13 that. So this is good. Now we can kind of put it all together, right? Because we could look at the ratio of the secondary to the primary field, okay? And for the secondary field, well, what do we need? Well, we need to get the information from the loop to the body, so that's M12 coupling. From the body to here, that's M23. And then there'd be a response to the quantity here, and that's going to be given by our response function. The primary field depends upon just going here, it's M13 here. So, I mean, the thing is, you look at these quantities here, and you can see everything happening that's physical, that's going on. And then this quantity here, our response function, has got a real and imaginary part that might look like that. So what is that? What is the system going to look like? Very often you've got things that look like this. You've got a transmitter and a receiver, and they're being pulled over some target. So if we did that and we had a target that looked like this, then as that transmitter and receiver goes over, you end up with a characteristic signature that looks like that. That signature is predominantly, well, it's entirely dominated just by all of the coupling, the way in which our primary field is interacting with with the target, and it has a couple of zero crossings. So there's going to be, as we bring this guy along here, so we bring it along here, there's going to be a zero crossing that's going to happen. Anybody have some suggestions about why you get zero crossings?
If you cross with your coils across the surface and along the line, then the direction of the fields in the transmitter coil are on one side in the same direction, and then at some point.
Right. Yeah. So there's a positive and a negative, and if the positive, if they're in the same direction, we usually plot it as positive. While if they're different, then we'll plot them as negative.
And when there's no coupling, then that's zero.
Right. So there's two zeros here. There's no coupling, and they're different. What are the situations in which you could be null coupled?
One of them is just above the other coil.
Yeah, so if I've got a transmitter that's sitting above here, then the transmitter is coming down, fields are coming down, so there's no coupling there. So now there's no currents. Okay, so in one condition there's no currents. In the other condition, there's currents, but we're null coupled because we're only looking at the horizontal component of the field. Right, so the coupling things give rise to this shape that's here. And then there's both the real and imaginary part. In this particular case, here's our response function, and we happen to be right at 1. So the real and imaginary, the black and the red, co-align. If I change that response function to be something that's less than 1, then I'm sitting on this side of the curve, and you see that the in-phase, or the imaginary part is actually larger than the real. And so when I look at what the response I would get, the imaginary part is larger than the real. So it keeps the same shape. It's just that the amplitude changes. And if I went the other way, had a large induction number, then the real is larger than the imaginary. Okay? In the time domain, we have the same thing, because the coupling issues don't go away. The coupling issues are the same in time as in frequency. So I'm going to end up with the same curve as I go through, but if I looked at different times, okay, I would see that at early times, I'm going to have larger values than at later times. I'm going to have smaller values. So things are just sort of going to decay. It's going to keep the same shape, but with different times, it's just going to decay. Okay, so that's kind of a quick overview to some kind of important aspects. The one thing here that's worth exploring for a number of reasons is that we've kind of introduced this circuit model, and we're thinking like, okay, that may be a good thing to really grab intuition of. It would be nice just to check to see, oh, is this really applicable to geologic targets? So here's a numerical test. Here was the coil, sort of coil model, and what we're going to do is to do a numerical evaluation where we have a transmitter that's directly above the target, and the target in this case is going to be a 30-meter radius 2 Siemens per meter object. 8 meters below the surface, and then we're going to measure a receiver that's sitting out here. When we do that, here is the results from the coil, and here's the results from the numerical simulation. And so you can see you've got that sort of same general character. So, you know, things are looking good, right? I mean, the thing that's beneficial about that is it just gives you a bit more confidence. Like, okay, if I first estimate, if I really want to try to estimate what might be happening, maybe I could just use the coils. The other thing with this is this has been developed with a what we call the SIL code. It's a two-dimensional cylindrically symmetric finite volume code. Lindsay is a primary author on that, developer. And what it allows you to do is to simulate responses from anything basically that's axially symmetric. And it's got a lot of uses. In this case, you can see how it could be used here, right? Because if you have your transmitter directly above, then along this axis, everything is axially symmetric. It's also very useful for modeling the effects of steel pipes, which are very much of interest these days. And it handles both conductivity and magnetic permeability. So it's just one of these codes that has got a lot of flexibility. And yeah, that's available and all programmed in Synthwave. So there's a couple of papers here at the bottom. Okay, so what have we learned? Well, we've kind of gone through some basics, and we've looked at a couple of coil apps for frequency time. The one thing we haven't talked about is getting the energy to a target and back again. So let's just take a brief look at how EM fields behave in conductive background. So let's just go back. Here's our Maxwell's equations in first order with our constitutive relationships. We can combine them into a second order differential equation. It's got a couple of parts. One is a diffusive part, and the other is a wave propagation part. And take the Fourier transform of those, and we can write them in this form here. But this quantity here is called the wave number, and it has that form. So here's our vector Helmholtz equation. There's the wave number. On the quasi-static regime, a more formal definition than what I offered previously, is basically that we're going to ignore this term compared to him. So he comes from that displacement current. So really k squared is just going to be equal to this imaginary part. And that then can be written in terms of this. So if we imagine a plane wave, so maybe a way to do that is to visualize, suppose I've got a current sheet up here. So I've got a magnetic current going along this direction. So I've got a magnetic field perpendicular to that, and the whole thing is propagating vertically down, and it's given by this type of representation. There's part of it has to do with a phase propagation, where beta is given by the square root of this guy. And the other end is the important one. There's also an attenuation part. There's an e to the minus alpha z. And if I look at how this propagates in depth, so this is depth this way, and this is the amplitude of the field. So it's at surface, and as it goes, as the field propagates to 1 upon e of its value, we're going to say that that's at a distance of 1 skin depth. And there's a formula for that given by. So skin depth is going to be an important concept. It's going to occur everywhere. And it's really that depth to which the field has decayed by 1 upon e of its value. If we look at the time domain systems, then there's a solution for that. So this is time as a well, this is time, and here's the amplitude. So if I if the whole Earth is uniform, you guys are uniform Earth, and I change the magnetic field here, then there's going to be a propagation in. And for instance, if we come back to Stephanie, initially when I turn this thing off, like there's nothing happening, and then gradually, as a function of time, she'll see a larger and larger amplitude of this magnetic field until at a particular time, 0.02 milliseconds, reaches the peak, and then it's just going to drop off. Okay, so you're just sitting there, nothing happens, then something comes through, propagates out, and you're. The other thing I could do, I could take a snapshot. So at some particular time after this wave has gone through, or is going through, I could just take a snapshot. And then here is what the profile of that magnetic field would be as a function of depth. There will be a peak here in this, and that peak is often called the diffusion distance, and given by this particular equation here. So the diffusion distance, so this guy is going to move inwards. So as time increases, this moves inwards. And that peak, that diffusion distance, increases with time, of course, and it decreases with conductivity. So the higher the conductivity, the slower the electromagnetic fields propagate in that development. So there's a plane wave app for that. You can experiment around and look at amplitudes and plot things in real and imaginary or amplitude phase. So now what's the effect of the background conductivity? So now we're getting a better understanding. So we've got a transmitter out here. That energy has to propagate into the target, and then it does all its time-varying magnetic field generating currents, and then those magnetic fields propagate back outward to the response. So let's just look at a few of these. Yeah. Can you guys see that at the back, or should we? It's okay.
It's okay.
Okay. So we've got a 2 Siemens per meter sphere, and it's got a resistive background. And if we look at the current densities, they look like this. So this is at a time of 10 to the minus 5 seconds. So you might ask, or at least I might ask, why are the currents like that? They're just sort of bound to the outside. I mean, why aren't they, why aren't they, like, you kind of got a wave that's coming in, why aren't the currents a little bit more populating on the inside here?
Magnetic field is larger on the upper part, and then the changes in the magnetic field going through. So because the electrical conductivity is the time derivative of the flux. And if you're closer to the transmitter, you have larger magnetic field.
Mm-hmm. But this particular point right here, if I can hold my, it's really got low values, compared to points out here. Right? So these are a bit farther away. Anybody else? Great.
The plane is propagating like a plane, not like a field. This one.
Well, it's true. We don't exactly have a plane right here, and we've got transmitted this. speed? Well, first of all, this is in time domain. This is 10 to the minus 5 seconds. Remember I talked about diffusion distance? Okay, and that diffusion distance depended upon the conductivity. So if it's high conductivity, it's not going to travel very far. So first of all, this wave that's coming in can't get in very far into this conductive material in 10 to the minus 5 seconds. And the other is that it's also going to be hampered by attenuation as it goes in. So what happens if I change the background conductivity? So now what I'm going to do, so this is almost like free space, 10 to the minus 8. Now I'm going to increase that conductivity. 10 to the minus 2. Not much happened. I increase it to 10 to the minus 1, and now some really interesting stuff has happened, right? So we've got currents being induced up here. So first of all, just to remind you, because we're not dealing in plane wave, so it kind of comes up. We've got a transmitter that is circular, right? And so it's going to have a magnetic field that is kind of different than a plane wave. And so right underneath here, there is going to be a kind of a void spot. So that character that's in here is, so inside the Earth, there's currents running into here and out of here. We'll look at those a bit more later. And that's what you see. But the takeaway point here is that now the conductivity of the Earth is starting to absorb a lot of the energy, and we're fading this guy out. And if I do one more, if I make this 1 Siemens per meter, everything, all the electromagnetic conduction is happening right up at the surface, and I'm simply not seeing the sphere at all. Okay, so that's the effect of the background conductivity on the object that you're looking for. If it's too conductive, you're simply not going to see through it. All right, so low conductivity, still low. Here it starts to really play a role, and here it's just dominating. So now I want to also look at this in the frequency domain. Okay, so we saw it in the time domain. And one of the things I really want you to take home at the end of this day is like, there's really no difference between frequency and time. When I first learned electromagnetics, like out of Ward and Holman, for instance, we had the equations, and then we first worked in the frequency domain, and you got some stuff, and then you did all that, and then a whole bunch later in time, like, oh, we got time domain equations. Like, what do we do? And everything was like so disconnected. It just, there just wasn't this connection. Whereas there should be, because it's just part and parcel of the same thing. And by the time you leave today, you're going to be thinking in frequency and in time, and I'll bet you that you're going to be thinking first in time domain, and then you're thinking about frequency, irrespective of what you're doing. Okay, so here is in frequency domain. Now we've got the same situation, and we've got a frequency of 10,000 hertz. If I change the background conductivity, make it a bit more, nothing happens. Make it 1 Siemens or 0.1 Siemens per meter. See, same thing. Induction here, kind of lost a little bit on the sphere, and increase it. It's just all up at the surface. So same thing, exactly the same pictures. So here's the summary. So what we got, there's a need to account for the energy losses. And so now we're ready to finally look at some field examples. So what are we going to do today? This is why you're here till 8 o'clock. Max. No, 7. We're good. Here's mineral exploration problem. Mount Isa, we've already seen that. We haven't seen this dam monitoring. That's really self-potential. For people who are interested, we could do that. We could do that tomorrow if people want. The example I'm going to show you, first of all, with inductive sources is mapping paleo channels for water in Denmark. We also have an example I'm not going to show unless people really want, airborne EM for near surface characterization, well, near surface, a couple hundred meters, to improve the velocity models for hydrocarbons. We won't do that today. Buprnong, this is a frequency domain system for looking at river salinization, so that definitely has some applications here wherever people are looking for fertilizers or nitrates or stuff like that in the soil. For a grounded survey, we've got the Deccan Traps. It's a large area in India which uses a grounded source. All the marine EM turn out to be grounded sources. So we've got hydrocarbon de-risking, which we probably won't do today. There's also a methane hydrate, which may not also be of interest. Here's one that will be, and we will definitely do this today. It's geothermal using magnetotelluric. And then there's a landslides using quick clays. It's kind of a combination of DC resistivity, ERT, and MT. Rock glaciers, so now we go to GPR. So we do rock glaciers. And there's also a really cool application of GPR for self-driving vehicles. Talk about that. That's really cool. And the thing I really like about this is one of those inroads where geophysics can impact in a very practical way with the average guy on the street. And the fact that we can make use of GPR for self-driving cars is providing more information in places where usual optical sensors don't work, I think is huge, because then people, if it actually comes to fruition and people start, having these particular sensors on their car and kind of think about, oh, I'm actually getting images of what's inside the earth and I'm using those to guide my car. I mean, how cool is that? And then it opens up the scope. Then it's not such a big leap for doing, another kind of EM survey to see something at a different scale. So there's kind of enthusiastic about that. And then we have a landfill. So this is with IP characterization, and we'll round up to that. So there's a few. Basically, we're going to do all of these except for anything connected with hydrocarbons here, unless people are interested. So let's do the inductive sources. Is this going to work? Oh, it'll find it automatically, right? We thought we'd done something. On my particular computer, this file has grown. When we started, so see, you guys are, I think you're number 14 or something like that in our presentation. So the very first one we had was in Denver. And at that point, there was a fair bit of stuff for EM in inductive sources, but it wasn't such a large, it still wasn't such a large file. It would open up pretty easily. As we've gone along, we keep accumulating stuff that should be incorporated. So now we have this huge folder for inductive sources. Sometimes it doesn't come up. We thought we had it figured out last night how to do this, but technology is quirky, especially for me. Okay. Here's our motivation. So there could be large areas. So why do we need something other than DC resistivity? Well, we've got large areas to be covered, so it's 100 kilometers. Maybe got some issues with respect to groundwater, high resolution near surface. We saw this shielding problem with a with the resistor. Minerals applications. Maybe we've got rugged terrains. I mean, you can imagine it'd be kind of difficult to do DC resistivity in these terrains. So a motivation to try to do something different. So I'm going to outline a basic experiment. We're going to do time domain EM with magnetic dipoles and then frequency domain. Let's see how far we get in the next 20 minutes. So there's some important questions. First of all, okay, what's the target? Okay, is that surface? Is it depth? 1D, 2D, 3D? Then you've got these usual things like, okay, my transmitter, where should that be? Surface, air. What's the waveform? What's the size? Now we got to worry about orientations, right? Because we understand about coupling. And then we got to excite the target. Again, that coupling issue comes in, geometry. Receiver in the data, what fields to measure, what's the instrument. This is actually a lot more complicated than DC resistivity. DC resistivity has some of these questions, but now when we're talking about EM, there's a whole host of things. And yeah, all of these questions, yeah, really kind of fall within the context of what's the footprint of a system and questions of survey design. So the basic experiment we've already been through, time varying magnetic field, generating currents, So let's go think about transmitters. So if we've got an area that's 100 kilometers on the side, we've got rugged terrain. I mean, you want to be talking an airborne system. Helicopter systems are by far the better if you can use them. Here's one. It's called a resolve system. It's kind of like the cartoon. It's a frequency domain system, and this is one time domain system. It's called SkyTemp that yeah is flown. Both of these are very popular. If you've got a deep target, these can be challenging to see. You're not getting enough energy down. So often what's done is you lay a loop on the ground, so big loop. So this could be a couple of kilometers on the side, and that gives you enough energy to find those targets. I'll show you an example of these. So time or frequency, either. Seismic, or the moment is the big thing. So it's the current times the area. And one thing I didn't mention is that you could have a number of terms. So it's that. And then the magnetic field looks like that of a dipole. The things to remember is that the fields fall off as 1 over r cubed. So you got that geometric decay, and that there's also attenuation. You want to be as close to the body as possible, so that means ground-based is best, if you possibly can do it, but sometimes it doesn't work. Helicopter is next, and then fixed wing is your third choice. And you're always worried about coupling. Measurements, either B or dBdt. Most times for airborne systems, you're measuring dBdt. There's a lot of work. In fact, Germany is kind of a leader in this field of doing superconducting flux gate magnetometers. So there's more and more we're seeing of high quality magnetometers collecting data. Traditionally, most of the data is still kind of coil data, dBdt. The receiver. Well, in the time domain, the primary current is turned off, and we get a response function. So the receiver could be mounted on the transmitter type itself. So this one on the SkyTem, there's a receiver down here. There's also another receiver up here. On this ground loop stuff, this one was really interesting, and I'm also pleased with that because you can see that we were the first people to actually invert these kinds of data. So there's a large loop on the ground, time domain, and these blue lines in here are the helicopter passes towing a total field magnetometer. Okay, so it's now measuring the total magnetic field in the air from a ground-based station going across here, and the images that it gives out of the conductor are really, really high quality. That's interesting. In the frequency domain, the big issue is the primary field is always on. You gotta contend with that. So you either kind of compute if you possibly can and subtract it out, or a lot of times what they'll do in these systems is have a bit of a bucking coil. So what this does here, it's another independent independent transmitter that produces a total flux through the receiver that's kind of the same as the primary, but it's going in the opposite direction, so it just sums those two things, and then effectively you're measuring just the secondary field that's coming from the Earth. Importantly for these things, you just need to know where the receiver and the transmitter are and keep everything in one unit. The resolve system, and I'm talking to a few other people here about land-based systems, are often just multiple sets of coils. So like this yellow coil here is 140 kilohertz, and here's its correspondence. So here's a transmitter, here's a receiver. Here's a transmitter, here's a receiver. So those are called coplanar systems. So transmitter, receiver, same thing. And you also could have coaxial, where that's what this guy is. It's like this. There's transmitter, receiver. So they're specially tuned. Each transmitter has got a coil that's especially designed for him. An instrument. How many people have used or seen an EM31? A few. So this is one that's very popular, at least in North America, from the point of view of site characterization for like real near surface stuff. Only has a single frequency, about 10,000 hertz, but it gives you something in the top couple of meters of what's there. Well, more important questions, right, have to do with our targets. That kind of does the transmitters and the receivers, but now always this issue, like where to collect the data, how accurate, depth of investigation, what's the footprint. So let's just do a little bit of that in the time domain to start with. So we're going to work with an inductive source system. It's going to have a current that's going to go off like this. And if we're measuring B, it's just going to decay. If we measure dB/dt, it's going to be a spike and then decay. So there's a couple of things that are associated with this, either before shutoff and after shutoff. And of course, there's that Dirac delta function here right at shutoff. So let's just take a look at the footprint. Currents are great, right? If you look at the currents, just gives you a great insight as to what's going on. We're going to look at a simple case of a loop source. So here's our transmitter. It's going to be 20 meters above the surface of the Earth. And it's called VMD because that's vertical magnetic dipole. Remember, I said that a circular loop gives rise to a magnetic field that's a dipole. And this one's going to be vertical. And that's our source. The geometry is going to be, at this point, a transmitter that's 20 meters above the surface, and then a homogeneous half space. And then our receiver, you probably can't see, it's a little red dot sitting out here. And so, first of all, some questions about, okay, where are the currents? How strong are they? how do they depend on conductivity, and what do the resultant magnetic fields look like? Those are all pretty essential, so we can explore that through this app. We've got abilities to look, so this is a 3D volume, so it's extending sort of 100 meters above and below the Earth's plane here. And as I said, we're 20 meters above. And we can look at things either in plan view or in cross section. So whichever field we want. So let's first of all look at the current density in plan view. So here's our vertical magnetic dipole. So the currents are always kind of going like that, right? So when I turn that off, the currents in the Earth, the induced currents in the Earth, are also going to look like that. Right? So they're going to be looking like that, and then they'll propagate outward. So on the plan view, what we see is at a time 0.01 millisecond after, the major part of the currents are actually out here. So right below the coil, there's nothing that's happening here. And then as you go outward, the currents increase. And at this particular time, that's where they are. And if I looked in the cross section, oh here it's terrible. I can't see it at all. But anyway, the yellow shows up. So the currents are going into the board here, and then they're coming around and they're coming out like that, right? So, like that. What about field lines? Well, first of all, you'd look at this and you immediately kind of get a sense of like, okay, where's the magnetic fields? Well, they're going to be most intense. So these are all loops that are coming in here, right? So magnetic field from the loop, strongest magnetic field is going to be right at the center. We've got that whole distribution. So there is the magnetic field lines that are associated with that, and then color coded. So here's the intensity. If we're up here, here's our receiver. That field line is going to be coming up pretty much vertical, and it's got a whatever amplitude it has. What about propagation through time? Remember I had that diffusion time given by this formula here. If I look at a very early time, which is 2 microseconds, the diffusion distance is about 18 meters. If I look later, diffusion distance 38, and later goes like that. So what I want to point out with this is that I have this loop of wire here. The moment I turn it off, I'm going to get currents that are transmitted, induced in the Earth, and they're going to be circular, right? And then those currents are just going to diffuse downwards and outwards. And that's what we're seeing here. It just gradually keeps going up. Like this. So these are associated magnetic fields. I think the currents themselves are more interesting. So what's interesting about that is the following. First of all, there was some very classic work that was done years ago by Misak Nabigian, who's a real pioneer in electromagnetic geophysics, and he was really trying to find a simple way that you could understand where the currents are and how they're flowing in the Earth. And he basically showed that, okay, you could represent the currents as a current filament, and that those, the high point or the maximum value of the peak would kind of go downward and outward with time. So here was his famous diagram that he had, and what we see is emulating that really quite nicely. That's what those dashed lines are here. They sort of follow that 30-degree angle that the filament currents are projected to go out. But you notice that the currents are not actually confined to a filament going downwards. There's a lot of current that's right at the surface, even though things are diffusing out. But the takeaway point here, and actually I need to remind you that we're seeing yellows here, but the amplitudes on these are very different. So in order to portray them, like this number here is 10 to the minus 7, that's 10 to the minus 8, that's 10 to the minus 9, right? So the amplitudes of all these things are. So that's the important points. Currents flow in the same plane as the transmitter currents, fuse downward, outward. Each transmitter has got its own footprint. There's a couple things about time gates here. The earliest, well, if you were going to try to assess resolution that you might get from a time domain experiment, what time channels would be most informative of that, and why? So somebody gives you data, a whole bunch of time channels, and you're kind of thinking about resolution.
What was the whole question?
Well, I'm just trying to kind of get at a couple of key concepts here. One has to do with resolution and resolving power. And at the very earliest times, you have the highest concentration of currents, and those are near surface. So if you were going to ask, like, okay, where are you going to get the best resolution, and what kind of scale of resolution are you going to get? You get a lot of information just from those early time currents, right? Whereas if you go to the latest time channels, and yet, like, what's the information that's provided? Well, really, that's kind of providing an overall depth of investigation. I mean, it's all kind of hand-wavy, but it's, that's kind of like the core. So at this particular time, you're still seeing stuff that's down here, maybe at 70 meters deep. So you could start to think about that as giving some indication of what your depth of resolution might be.
But at the near surface, isn't there like a problem with the overlay of the turning off of the transmitted signal in time domain?
Perhaps, can you elaborate? So why is there a problem? Sorry.
I thought because of the turning off and the ramp for the signal to go down.
Yeah, no, that's a very important point, actually. So this is all kind of theoretical, but in practice, you're going to try to turn that current off, and that, from an instrumentation viewpoint, is can be challenging, especially if you've got a big current and big moment that's in that transmitter. So there is some limitations that come about because you simply can't turn that thing off fast enough. We'll talk about that a little bit in the case history for the casting. Yeah, so I guess those were the main points. The perhaps more interesting question here now is, let's complicate the Earth a little bit, and let's make an intermediate layer in here. So we've got 100 ohmmeters, but a 20-meter thick layer of resistivity that could be highly resistive or low resistivity compared to the background. So we might just think for a second what that might do. So first of all, we've got an Earth here that's just a half space, and here's what the currents look like. Now suppose that I'm going to make a resistive layer in here. So I'm going to make it 1,000 ohm meters. Okay. So if I put in a layer 1,000 ohm meters, what do you think is going to happen? How are those currents going to change or not? Anybody? I keep going. Yeah.
So in time, I mean,
yeah.
by
So
propagating downwards through the resistive layer. Sure. That's what you.
Yeah. So do you think if I put a resistive layer in here, if I'm looking for something underneath it, is it going to affect what's happening underneath or not? Just any kind of guesses as to, okay, I'm going to put in a resistive layer in here. What am I expecting now my currents to look like?
I think the current propagates slower.
Slower where?
Slower in depth. So the image in depth is not as good as before.
Okay. Yeah.
Well, I would expect that they stay longer in the conductive zone. So the current will be more or less focused in this conductive zone and will stay longer, will not propagate much deeper.
Okay. Anybody else?
I would expect that there's certainly no currents induced in the resistive layer, but below. Again, more. So below the resistive layer. I don't know.
No, that's good. No, there's a lot of bright things. I just didn't want to prejudice things one way or the other. So let's look. So this is exactly the thing, right? This is why, you know, if you force yourself to think like, okay, I'm going to do this. What's going to be the consequence, right? And before you press that button, really put your neck on the line and say, okay, I think this is going to happen. I think this is why it's going to happen. I think that it's going to show this or not. Okay. Then you press the button, and you get this. So that actually is pretty much in accordance with what at least a couple of the comments were. So here's our, you know, the background of 100. Here it is. And here's our resistive layer. So there's no currents in there. What about the electric field? Have we lost electric fields too, or? Right. We haven't lost electric fields are still there, but we're not getting currents. Ohm's law says J is equal to sigma E, so there's no currents there. But also that means there's no energy loss. So this is interesting, right? Because there's no energy loss in here. So there's information that's coming down here. Now it sees this resistive layer, and it goes all the way through. No energy loss, and you actually see better at depth than you did here. It's a little bit hard to see with that. So that's kind of interesting, I think, right? Just you have a resistive layer up here. It actually helps you to see farther. And you know, when you think about, you know, energy losses and stuff like that, it sort of all kind of makes sense. But these images help. Now, what about a conductive layer? So we're kind of all prepped for that. Conductive layer? I'm gonna need to feed you guys pretty quickly. It's just like.
Then there are more currents in use in there, and but the field is attenuating faster and below the eddy currents might be a bit smaller than compared to this picture.
Perfect. You get a gold star. We forgot to bring our gold stars. Okay, now, maybe I'll ask the department if they've got any stickers. Start handing out gold star stickers. Yes, there we go. So now you can see actually that the currents have really, they really concentrated in this conductive zone. So in relative to what was up here before, you now have much more sensitivity to what's going on here. So now it's like you're kind of focusing in on the conductive target, and then you're not seeing anything at depth. And if you make it really conductive, that's it. That's basically all you see. You just kind of blast your way through the big hit on the block. It's just a conductive region down here. And then you're not getting all the way through here because it's attenuating. If we look at the magnetic fields from these three cases, the half space, the resistive, the conductive, you can see how the magnetic fields are changing a lot, especially in this region in here at the resistor or the conductor. From the point of view of extracting information, remember we're sitting up here someplace. So from the point of view of extracting information, the thing that we're interested in is what the sounding curve is, what the response is as a function of time. And if we look at a half space response, it looks like this. So this is our response as a function of time. That's what it is. If we put in the 1,000 ohm meter, the layered earth is this dashed line. So it's hardly any difference, right? So you know that if I have a sensor sitting up here, that's going to be real tough to find that. On the other hand, if I put a 10 ohm meter layer in, look at where that response is. It's more than half an order of magnitude different. And, well, if I make it a 1 ohm meter layer, I got like 1.5 orders of magnitude here difference in that sounding curve. So you can tell by looking at this, if you've got an inductive source system, if you've got something down there that's conductive, you have a good chance of seeing it. If it's resistive, probably not very easy. Here's an example over a conductive sphere. So now what we're going to do, this is getting closer to what you'd see in practice. You've got an area out here, so each of these dots is going to be a receiver. So we'll do the sounding at each of those. And at very early times after shutoff, okay, the response is basically the same over the whole region. So the depth here is about I don't know, 10 or 12 meters to the top. We're sitting, this actually, sorry, I forgot to say, so this is a plan view section, and then this is a profile right across the middle. If we did that profile right across the middle, we've got this conductor in here, and yeah, those are our locations. So really the only thing we see, the values are just constant. We're just seeing the top region. If we go a little bit later in time, now the fields have time to diffuse through, and in plan view, then they look a little bit like this. So you're starting to see that response come out. Profile looks like this. Here's the sweet spot, about 0.3 milliseconds. Plan view map. Here's the profile. And then as time decays, or as time progresses, everything decays, and you get this. So as a function of, so as a function of time, you see that the plan view maps start right at surface response, so you don't see anything. You gradually see the sphere, currents in the sphere build up, then they gradually dissipate and you're back down to normal. But you've got many orders of magnitude, probably 5, 6 orders of magnitude difference in that response. And usually, this is what you'll often see from contractors. They'll provide line plots, across a profile of how things work as a function of time. So very early times are up here, very late times are up there, and you're looking for some kind of a sweet spot where you've got anomalous signal that would indicate a conductor. So time domain systems. Here's one. It's a SkyCam system. It's got a low moment and a high moment. And this, I'm sorry, your name is? Yeah. Christine. Christine. Okay. So this was a point that Christine made just a while ago when I was talking about what we'd see immediately after we turn things off in resolution. And she said, well, you have trouble turning the system off. And that is exactly right. The SkyCam now operates with a dual transmitter source. One is a low moment source, and because it's a low moment, have a low current, they can actually crank it off more quickly, and they can measure as early as 12 microseconds with their system. Okay? Then and that's great for seeing the near surface structure. Your highest resolution is going to be at the earliest time channel as possible, and that cranks it back to 12. If you want to see deep, you need moment, right? And so they then have a high moment system that, they try to crank it back, but the earliest time channel they can get is 47 microseconds. And then, so here's the waveform. It kind of goes up and ramps down. Okay. This goes up, ramps down. And then you measure different times long. The other system that we'll have reason to look at is something called a VTEM system. So now it's sort of an outer loop for the transmitter and an inner loop for the receiver. They use a different kind of waveform. So it's more like a helitem waveform, and has a much gentler ramp. You turn it off, and then goes like that. Kind of the same, a little bit different. But from our perspective, you're putting in, you've got a waveform, crank it off, and then measure things out.
So what was the earliest time channel for the second system?
Oh, for here? Actually, good question. I'm not sure. Let's see. Oh, it'll only take 5 minutes. This would be a perfect place to quit. So if your stomach's not grumbling too much, let me do this. I'm going to do case history. Okay. So we're going to do one case history on groundwater. And it comes from Denmark region. The setup here is that it got local geology. It's got all these kind of incised valleys that were filled in with various sands and gravels, and there's some clays in here. But the big thing is that there's like a Paleogene clay underneath here, and the clays are really conductive. And what they'd like to do is to try to find that kind of nearer surface structure that would potentially hold all of the aquifer water. And really their long-term goal here is to get serious about, okay, what happens if I draw water out of here? Where's the water coming from? Is it coming from down below? Is it from the side? Is it here? Or if I have two wells, so if I have a well here and if I have a well there, and I'm going to pump both of those, do they talk to each other? Where's the water connection? Everything is buried and hard to see. So it's really much more driven by a groundwater hydrogeologic problem than it is for the geophysics. and which is actually kind of what I like, because geophysics is just an incredible tool for providing information, but it does not really answer the problem. And I think this is a nice example of that. So yeah, here's the area set up in Denmark. What are we worrying about for physical properties? Well, basically, we've got a lot of buried valleys in here that we want to try to find. There's conductive clays underneath here, sort of 1 to 40 ohm meters. Water-bearing sands up here, these are greater than 40 ohm meters. So it's a pretty simple kind of thing at some level. We're basically trying to find the depth to the top of a conductor. So the clays underneath are conductive. If we can find how deep those clays are, then we've got basically that upper structure. So that's basically the goal. So now what we're going to do is fly the SkyTemp system with a low moment system to image the near surface, high moment to image the deeper structures. And the flights lines are like this. And the data, so there is 333 line kilometers, 100 meters line spacings. And they have to remove some stuff because it's noisy. So just like you were talking about, lots of cultural noise. But you're still left with lots of data. And then you're going to invert those data. You could go ahead and invert them in 3D, but there is also potential for inverting, just using 1D analysis, but maybe using information from adjacent soundings just to prevent things from getting a bit too wild. So they call it laterally constrained inversion. So 25 layers. So it's kind of a 3D, sort of a quasi 3D. So that now gives them a volume. Okay, and now you could take a slice, let's say 5 meters above sea level, and then look to see what you got. And so this is the resistivity on that slice. So it's resistive here, kind of follows resistive there, and then up here. So the blue are conductive, and the reds are resistive. So of course that's what we're looking for here. And you can also use that same model to see, okay, how deep do I need to go in order to hit this clay or hit this high conductivity. And that's what this is. So this is the elevation of that interface above sea level. And these numbers are all negative. So that means that the deep channels are these blue things. So that's very important information to try to figure out where those are. But they can take it one step further. Now we've got those depths to the top of the clay, and they've also got a number of drill holes that they put in, and so they made some proxies with respect to conductivity that they're getting out and different units for the geology, where some sand, whatever else, right? And then once they've got that, then they can attach hydraulic conductivities to these. So in the end, what they do is they get a 3D volume, so a hydrogeologic volume in which you've got the hydraulic conductivity. So that allows you now to do like a mod flow type of example where you actually look to see what happens if you've got this. So we've got this information. It's made a whole bunch of valleys that kind of crisscross, attach hydrogeologic properties to them from a lot based on the electrical resistivity. And then they did the interesting experiment of taking two regions here that took a well here and a well there, and they just drew water from those and then looked to see, okay, where is that water coming from? And yeah, you can see that there is the water from here is coming from there. Water from here is kind of coming from around, and that there's almost some communication between those two wells. Good. Now, so are you hungry yet? I suggest we let us take a break for an hour. Meet back here, and yeah, then we'll continue on. So we're starting to get together, starting to get to the point where we've actually done a fair bit of the fundamentals. Then the next one that is that we're going to tap is it's really interesting because it puts together the two things that we've talked about: the DC resistivity with all the charges and currents, right, and the inductive source, right? We're now going to put those two things together with a grounded wire. And then to look at, we're going to parse out, okay, the effects of the wire, the effects of the ground, and just really start to see what's going on. That is going to be the source for all of the things like the marine EM. It's the source for all kinds of things that are done on the ground. So then we'll hit that first thing after lunch when your stomachs are full and your mind is buzzing around with excitement. Maybe. Okay.
If you want to leave stuff in here, that's okay. So we're going to lock the room. Just
oh, perfect.